This one?
Yeah.
Okay.
So what is that other stuff?
So this is this guy.
This guy.
Yeah. And then we have the one on the desktop.
We can hear us too, by the way.
first speaker today is Timothy Hallman from DOE, who will present on opportunities for nuclear physics.
Thank you, and thanks to the organizers for the opportunity to come and speak. I always enjoy coming to these user meetings, and it's a sort of nice chance to talk to the community and take questions from the community. So I'm going to give a few comments on frontiers, challenges, and opportunities for DOE NP stewardship of U.S. nuclear science. And the clicker is clicking. Which is fine if there's something over there I can press. There it is. Excuse me? Well, maybe there's a. Wait. Here we got it.
We got it.
So I piloted it. They didn't cover that at Johns Hopkins where I went to school. So there are three broad, as we know, or as you know, there's three broad scientific thrusts of nuclear science. Quantum chromodynamics seeks to develop a complete understanding of how quarks and gluons assemble themselves into protons and neutrons. Nuclei and nuclear astrophysics, seeking to understand how protons and neutrons combine to form atomic nuclei, and fundamental symmetries. And I would say clearly the focus here, of course, is the quark structure of nucleons and nuclei, but actually the program at Jefferson Lab has components which touch on all three of these main thrusts of nuclear science. We are the primary provider of support for nuclear science in the United States, and this gives a visual representation of what we're responsible for. In the blue circles, you see the university principal investigators. The amber triangles are the user facilities, which I'll say more about in a moment. We operate 5 centers of excellence, some smaller facilities for special purposes, and quite a substantial nuclear science workforce. That's just the people who have directly supported, but if you include the people who also are indirectly supported by nuclear science who help ensure that everything can work right, it's a workforce that's about 5,000, I think, in between 5,000 and 10,000. So it's a very substantial portfolio. We operate 3 so-called microscopes for pursuing groundbreaking research, the Relativistic Heavy Ion Collider, CVAP, of course, and the Argon Tandem Linac Accelerator System. And I'm going to take a brief tour around, spin around the portfolio, if you will, and say a few words about each of those, including a new one that's under construction at Michigan State University. Of course, everyone here is well aware of what's going on with the machine, the 12-JLab upgrade. And this shows some of the main components of the upgrade, the new central helium liquefier, the new cryo modules, and Paul D. As you know, this project is well along. This is an old slide now. It says more than 92% complete. I'm not sure what the current percentage is, but it's more than 92%. I've likened this to this project to a big ship that's made a very long journey and is now coming into port and is about to dock. And I think I would characterize it as being about 500 meters offshore at this point. The crowds on the shore are cheering, and the people on the boat are happy to imagine docking. And we just need to sort of bring it gently into the dock and with a successful finish. and things are going well in that respect. When it's complete, the new physics that will be occasioned, the search for exotic new quark and anti-quark particles to advance understanding of the strong force, evidence of new physics from sensitive searches for violations of fundamental symmetries, and a microscopic understanding of the internal structure of the proton, including the origin of its spin. So this is a picture of Hall D some time ago. If you have a really keen eye, you'll see that the center here is empty, but that just tells you that this is an old photo, because if you look at more recent popular literature, you can see that in fact the center is now quite filled. And in fact, there are initial, I'd say, calibration or engineering data coming out of Hall D that look very, very promising and encouraging. This shows the reconstruction, for example, of this 3-particle decay. Omega goes to pi plus, pi minus, pi 0. It's just an indication that Hall D is really positioned to deliver on the promise of allowing us to study in detail for the first time these exotic mesons that will give us a window into the excitation of the gluons, which we haven't been able to do in detail before. And that combined with the strength that's coming from lattice QCD promises a brand new watershed of understanding of how the strong force works, how QCD works. So very exciting. This is not by any means to feature only Hall D. There's tremendous work going on in all of the halls, A, B, and C as well. But this one happened to be just one that I picked up, and it has some engineering data that's very beautiful, so I thought I would show it. The questions that will be addressed by the 12 JLab upgrade, the role of gluonic excitations in the spectroscopy of light mesons, I should say exotic light mesons, missing spin of the nucleon, is there a significant contribution from valence quarks, valence quark orbital angular momentum, whether we can reveal a novel landscape of nucleon substructure through measurements of new multidimensional distribution functions, DMAs. What is the relation between short-range nucleon-nucleon correlations and the platonic structure of nuclei? And can we discover evidence for physics beyond the standard model of particle physics? So I think in a short summary, this upgrade project is going extremely well. We expect to finish on time according to the rebaseline plan. And so this community should be looking forward to a real exciting period of new science using new tools and a new accelerator. And I think the future is very, very bright for the program here. And that's, I think, a very exciting thing for the community. Of course, longer term, there are other instruments that we need to provide to take full advantage of the 12 JLab capability. And one of those is the Mahler detector, which will look for parity violation and as an indication of where the standard model may break down. Mahler has had a successful science review. I think in a word, the ball is in our office's court, NP's court now, to define the next steps to continue progress. The science committee that reviewed this compared the results of Mahler that will come, provided they can achieve the precision that they said they can achieve, to something like G-2. So it's something that will stand as a benchmark that any theory that purports to understand deviations from the standard model will have to address, and if they can't address the measurements of Mahler, then that will very much discourage that theory. So a key question is, can they in fact achieve the precision that they say they can achieve? Presumably the answer to that is yes, but I think a reasonable next step will be to have a technical feasibility assessment to make sure that we're confident that there's no unforeseen issues that would prevent them from doing that. So, but that'll be, I think, something our office has to work out with the PIs and with the Jefferson Lab management, say, in the coming weeks. Beyond that, of course, there's the solid detector, which is another large initiative for science of parity violating deep inelastic scattering and deeply virtual complement scattering. This one is also, there's a great deal of interest and progress. And I know there's been a laboratory director's review of this that was quite energetic, and the reports that I got back from the medium energy program manager were very impressive in terms of what's already been achieved and the international interest in this project. And my comment to this would be, when I think of this project, subject to the constraint, as always, that it has to go through the process of having a science review, a DOE-sponsored science review, and certain other steps. This is certainly a detector that's in JLab's future, and so the question is really the timing of when we can make those steps and finding the resources to do it. But I don't think there's any question about the value this would add to the Jefferson Lab program. A little north of here, of course, there's another laboratory. So now I'm going to take the gaze around the rest of the program. A little north of here, of course, there's another laboratory interested in hot QCD. If I can use that term. Rolf's not in the audience, I don't think, so Rolf objected to hot cold QCD.
No, I'm here.
Oh, there you are, okay. Sorry, Rolf. See, when you speak, you sort of look to the back of the room. So.
We didn't like the cold QCD.
Ons zegt koelkjes niet.
Okay, well, I apologize. So, of course, what their continuing mission is to understand the properties of the matter that they discovered a little while ago, a perfect liquid of quartz and gluons. And the signature discovery there that tells you that something absolutely new and fundamentally different is going on is a phenomenon called jet quenching. Normally when you have a hard scatter of a quark or a gluon in high energy physics, you get back-to-back jets on either side of the interaction. And in heavy ions, it's well known by now that you see one jet on one side, but the other jet that has to go through the dense matter, this perfect liquid of quarks and gluons, has its energy redistributed in much softer modes, so you don't see the jet, or you don't see it to the same extent as you would in a proton-proton collision, for example. And that's, I think, the signature discovery of Rick that tells you something fundamentally new is going on. Rick continues to research the properties of this matter and is at the top of its game, as well as JLab, in terms of integrated luminosity focused on that research. And so in 2014, they integrated more luminosity in that run based on accelerator improvements that they've made from our operating funds. More luminosity in 2014 than they integrated in all the previous runs combined. And so this accelerator is performing extremely well. No other facility in the world, existing or planned, can rival Rick in its range and versatility. That includes the LHC as a heavy ion collider. It is the only polarized proton collider in the world. The questions that they're addressing is what do we need to know about the initial state? There's a mystery of sorts. People are reasonably well concluded that very early in Rick collisions, there's a thermodynamic state of quarks and gluons, that they are deconfined and there's a thermodynamic state, but they don't understand how that thermalization happens so quickly. And one of the keys to that is understanding what the initial state in the relativistic heavy nuclei is. And so that's one open question, which also bears on the motivation for a future electron-ion collider. What did the data tell us about the initial conditions? What is the smallest collision system that behaves collectively? There's a great excitement in that community because it appears that even in rather light nuclear systems, deuterons on gold, for example, or very light nuclei, that they still see the same type of phenomena that they see in heavy collisions, collisions of heavy nuclei. And so the question is this perfect quark-gluon liquid actually produced in these other collision systems, and we just didn't see it before, or is something different happening? So another question, what the QCD phase diagram looks like. Is there a critical point in the hadron gas QGP transition region? What can jets and heavy flavors tell us about the structure of the strongly coupled quark-quark plasma? What do quarkonia and other data tell us about quark deconfinement and hybridization, and can there be unambiguous proof for chiral symmetry restoration? So that's their physics agenda that they continue to work on. Another physics front at RIC, as at JLab, is understanding the origin of the spin of the proton. And the contribution recently from RIC is based on this type of asymmetry. This is a double spin asymmetry, which is in a kinematic region where it's proportional to the gluon polarization times the quark polarization. This is looking at the asymmetry of dijets. And what one concludes out to a region where RIC covers, which is about 0.1 or 0.2 in Yorkane X, is that the curve looks something like this with this red uncertainty. And if you naively follow the curvature on out, it would suggest that the gluons may account for quite a significant fraction of the proton spin, maybe 50 or 60%. Of course, there's still a very large uncertainty here to be narrowed down, and that's another motivation for a future electron-ion collider. But this is a very important result because previously people were completely unsure what the gluon contribution to the proton spin was and thought perhaps it was even zero or perhaps even negative. So this is an important insight already, and work continues. Where's the future for both QCD programs at both facilities? is looking forward in the future to an electron-ion collider focused on understanding the glue that binds us all. So protons and nuclei and black holes are the only fully relativistic, high enough energy density to excite the vacuum stable bound systems in the universe. Protons are fundamental to the visible universe, and their properties are dominated by emergent phenomena of the self-coupling strong force that generates high-density gluon fields. And so this program would focus on the mass of the proton and how that's generated dynamically by the quarks and gluons inside it, the spin of the proton, the dynamics of quarks and gluons, and the formation of hadrons from quarks and gluons. So in this audience, I'm sure you're very aware of the science case and are working to even strengthen it further, and are, as we'll hear in a moment, are working very diligently on a possible design for a machine that would address this science program. Moving to the Argon Tandem Linux Accelerator System, this is a venerable old machine, which at this point is the only DOE-supported facility for providing science opportunities for nuclear structure and nuclear astrophysics. And the recent addition to this capability on the front end is Caribou, which stands for California Rare Isotope Reader Upgrade. This is basically a way to make a poor man's radioactive ion beam, catching the fragments from the spontaneous fission of californium and in a gas catcher and then re-accelerating them down the beamline for scientific research. The result I'm about to show you that uses Caribou beams was developed using two pieces of instrumentation. One is Gratina, which is gamma ray tracking, so a array of modules which have germanium in them, but they provide not only energy information but tracking information, so you can assess the direction of the photon before it's impinged on the detector, and therefore you can project backwards and correct for the Doppler effect, which gives you the best resolution possible. That's used in this study in combined with another detector, which is a highly segmented detector around the target for detection of particle fragments, and that's called CHICO-2. That's this thing right here. And so this is a result from that combination of instrumentation. So this is taking radioactive species that come from the Caribou front end, looking at their time of flight so you can separate them and tell what they are, and scattering them off a lead target, looking at the fragments that are produced in CHICO-2, and then gating on that to look at the gamma ray spectrum in coincidence. This is the coincidence spectrum. And the one of interest in this particular study is 146 barium. And the reason that's of interest, A, is because it's a neutron-rich radioactive ion. And there's great interest these days in going as far from the line of stability as we can in the direction of neutron-rich. That's because that's where we think the rapid neutron capture process is relevant, and that's the process we think is at play in things like core collapse supernovae, perhaps neutron star mergers that produce the heaviest elements in the universe. And so this is a step in that direction, 146 barium. And the interest is that it's predicted by theory to be octopole deformed. So the gamma ray spectra are being measured in order to determine whether that's in fact true. And in fact, if you look at this little peak here, which doesn't seem to be so big compared to the others, it's actually very important. This is based on 3 days running, and so the statistics can be much better with further running. But this is a 7 minus the 5 minus transition. It, in fact, is the peak that's going to allow us to extract an E3 transition probability to verify the theory, and in fact that 146 barium is octopole deformed. So this is part of a whole campaign to understand the structure of these neutron-rich nuclei and ultimately nail down the site and location of the R process and other processes important for what goes on in the cosmos. Of course, the future of nuclear structure and nuclear astrophysics in DOE perspective is the future facility for rare isotope beams. And this was the picture a little over a year and 2 months ago There was an august panel of people there with shovels in their hands. It was very ecumenical. There were Tea Party members, there were Republicans, there were Democrats. Everybody came together because we needed somebody to shovel. And so that was the picture. And what I wanted to point out more than the people with the shovels is that the only thing that was there at the time was this sort of green golf mat. There was nothing. There was no hole, there was no construction going on, there was nothing. When you look at that today, okay, Fripp construction I would liken to a speeding freight train. So this is the picture, well, a little while ago, you see the construction profile. If you look at it 7 o'clock this morning, which you can see is a bad time to look because the lighting is not very good from their live camera, it would look like this. I think you get a slightly better picture here that this tunnel has already been completed and structural steel is going up for the surface buildings. And so this project is truly well along in its construction. Ultimately, it will provide access to about twice as many nuclei with observed properties that we know about at the moment. And the real interest there is not just stamp collecting and collecting more isotopes, but collecting ones that are neutron rich and also getting enough systematic data that we can understand and improve our theory and give it even some predictive capability. They, of course, are interested in new instrumentation, as you are here at Jefferson Lab. So Greta, SECAR, the separator for capture reactions, and a high rigidity spectrometer are high on their list. They are also tooling up, I would say, to have a robust theory effort to support the experimental program and working out those details. And the name of that they've captured now is the Fripp Theory Alliance. And so if you want to know more about any of those things, you can ask me in the question and answer period. The follow-up to Gratina will be Greta. I showed you one result from Gratina. This is another one for a capture reaction important to understanding X-ray bursts, which are among the most energetic explosions in the universe. This particular result came not from ATLAS, but came from the National Superconducting Cyclotron Laboratory, as Gratina is a detector that travels from laboratory to laboratory based on where the most exciting physics campaign is. The reaction was studying capture of a proton by 57 copper going to 58 zinc, which doesn't seem perhaps so exciting, but is very important for understanding these X-ray bursts. As you know, there's a long-range plan in progress, and one of the priorities clearly indicated in the discussions there was neutrino-less double beta decay. That's a process where we have a nucleus with with Z protons and neutrons that decays to something with Z plus 2 protons, N minus 2 neutrons, 2 electrons, and no neutrinos. This is forbidden by lepton number conservation as far as we know. If it's observed, it would give us access to some very important science questions, such as whether the neutrino is its own antiparticle, why there's more antimatter than matter in the universe, and perhaps even most importantly, what is the mechanism that generates the neutrino mass, and why are those masses so much smaller than those of other elementary fermions? And so we see here the quark masses, the neutrino masses are, to our knowledge, much smaller, and why that is completely not understood at the moment. So we don't even know, for example, we think we know that there are 3 neutrino masses, but we don't even know which are the heaviest ones and whether we have a so-called inverted hierarchy where inverted hierarchy where 2 of the masses are greater than the other one, or did I get right, Bob? That's right, okay, or a normal hierarchy, sorry. Somehow I thought it was on the slide, I was looking for it, I didn't see it. So the sensitivity we have to reach in this effective mass.
It's on the slide, Tim. It's IH and NH in the green and in the red.
Thank you. I thought it was on the slide. Will depend ultimately on, or can be aided, I would say, maybe not depend, but aided greatly by experiments like the one at Ash River, which could give us a hint of what the hierarchy is, and experiments that also may tell us what the lightest neutrino mass is, so we know exactly where we land in this particular panorama, which hierarchy we have and where we are. And there are experiments planned, like Project 8, which may get us down to an effective neutrino mass, or excuse me, lightest neutrino mass of 40 milli-eV. 40 milli-eV. So anyway, this is going to be a very high priority, very exciting campaign in nuclear physics in the future. Let me skip that. Ultimately, the sensitivity, or the half-life sensitivity that needs to be reached is about 10 to the 28th years. And this just shows the international competition, which is very stiff, even at the stage of demonstrating feasibility for the sensitivity that's required for a large-scale experiment. So I think I'm running out of time. Nuclear theory is very important. We've put out a new FOA for theory topical collaborations, and that's underway. You can ask me about that if you're interested. And we continue to produce isotopes in short supply. I will skip that as well in the interest of time. Let me skip that. And just come to quickly the budget issues. So in the President's request for 2016, the request for research is up about 13 million. And that's spread more or less evenly over all the different subfields. For operations, there's a similar requested increase, and I'm happy to go back through the details of any of these, but I'm trying to respect the time. And so overall, the request for nuclear physics in fiscal 16 is up about 29.1 million. So I haven't shown it here, but of course the two houses of Congress weigh in on what they think the correct amount should be. In the House of Representatives, the President's request for nuclear physics was cut by $8 million, but very importantly, the requested increase for research was sustained, so that's a very good thing in the House mark. In the Senate mark, the mark by the Senate was $33 million below the President's request, which would make it about $3 million below the 2015 appropriation. And so the things, to first order, we don't know how we will deal with that if it comes to pass, but the things that you just saw, the increase for research, the increase for operations, and other things, you can see that there won't be money to address those if we're down by $33 million and we're even behind where we were in fiscal 15. So it's a serious issue that needs to be resolved by the two houses of Congress. We're in the middle of a long-range plan. JLab is playing a leadership role there. And aside from the discovery science portfolio, I'd like to mention that there's an NSAC isotope strategic plan being put together under Larry Cardman, and so that leadership is appreciated as well. This just emphasizes that the discovery horizon in nuclear science is very broad. It goes all the way from a few microseconds after the birth of the universe all the way up to the present day, and so we have a very exciting outlook. And so finally, I would say the CBAF and RIC programs are both unique in the top of their game, with compelling must-do science in progress are about to start. Long term, the future for both programs will center in our present vision around the future electron ion collider. Very high priority, as I said, in evidence at the long-range plan was not losing leadership in the science of neutrinoless double beta decay. And an equally high priority is going to be increasing investment in research and projects as a percentage of the total energy budget. Thank you. Sorry for running over a little bit.
We have time for a few questions.
So let me start by saying that I actually like the slant you've given on many slides. You clearly have worked on it since the last I've seen it. So I like many of the slides.
Is that a polite way of saying the previous talks were really
No, that's not polite at all. I just felt that you clearly have folded in some of the recent discussions. So
I tried.
It was very nice to see how you portrayed some things. So I'm going to ask you a little bit about the RIG spin result. The way you mentioned it was completely fair. However, it's very misleading to quote a number like 60%. Any number there. I mean, look, that delta G is that we have indication delta G is positive in the reach of X is very good. That's clearly progress. On the other hand, it shows you that delta G can be non-negligible in large X region, can be non-negligible in the small X region. Any number, to quote any number, is dependent on the model we're using for it. And we've learned from carbon distribution features that that's a very dangerous game. So I agree with the slide, I chose progress, but to associate it with any number like 60% is a dangerous game.
Yeah, I agree with you completely, Rolf. And so I think I was reflecting their numbers that they may have said in some presentation, but ultimately sort of where that will wind up is to be determined. I agree completely. I think for me, the biggest advance is we've gone from thinking that perhaps it was completely negligible to thinking that it's some number that's significant. But as you say, it's also a question of what X range you're testing. And the RIC results clearly are only relevant in a range that's fairly narrow. I mean, you guys are sort of at the high X end, but there's also a lot of territory at the low X end that we have no idea about. And so the thing could turn over and go negative for all we know. So I agree with you.
My question is kind of out of somebody that hasn't really been following this very much, but in terms of the neutrino-less beta decay, what's the progress in terms of understanding for the funding of it, and where would we select the site, what the status of that is?
Yeah, so just as a quick status where we are, and it's clearly sort of a long progression process, well, not long, but several steps need to be made. So we've asked NSAC previously, an NSAC subpanel chaired by Bob McEwen, to establish down select criteria. What would we judge candidate technologies on to decide what might be the best choice for a large scale, ton scale experiment. And that was a previous exercise, and then we've charged them again to take a look at essential R&D that needs to be completed by those candidate technologies to be competitive for that ultimate decision when it would be made. So, and Bob is again going to chair that, and they're tooling up that subpanel in order to get ready for that. So we imagine that a down select would happen sort of in 2 or 3 years' time. And in the interim, we're trying to, and we being the NSF, the nuclear physics DOE and high energy physics DOE are working together to try and understand what remaining essential R&D questions there are and pool our resources to cover those as best we can. So in the next 2 or 3 years, we imagine to be finishing up, if you will, the R&D on the essential questions. And then there would be sort of a real exercise to understand best choice for a big experiment and what we want to invest in collectively. And as far as funding, I mean, that's our sort of long-term vision, but I would say, that's still a future prospect. So there's nothing sort of designated at this point beyond some resources for the R&D that needs to be completed. So, I don't know, does that sort of say it? I can say more if you ask me offline, or at least clarify those things.
Okay, one last question from Mon, and then we'll move on.
So, Tim, you and I have discussed a little bit, and I've given my opinions to this community. Can you make a few comments about the potential for international participation in these big projects like neutrino-less double beta decay and possibly electron ion collider?
Well, I can make remarks about the desire for it. I'm not entirely sure about the prospects for it. But so when we think about neutrino-less double beta decay in a very, very large experiment, we're not really sure at this point what it would cost, but it's clearly in the several hundreds of millions of dollars. And the future electron ion collider, there was a NSAC subpanel that looked at that and thought that, roughly we might be thinking about $1.5 billion for such a facility. These big mega projects get into a scale where it may not be possible for one region of the world, say North America or Europe or Asia, to do these kinds of projects all by themselves, and therefore they may need some global cooperation and collaboration. And so we're interested in trying to pursue that. And in fact, as Mont knows, there's a nuclear science symposium tomorrow where on the margins of that meeting, there'll be some funding agency representatives there. We'll certainly be talking to them about interest in collaborating on some of these projects. For neutrinoless double beta decay, I think it's the scientific wisdom is that the world, not necessarily the United States, but the world needs at least 2 of these. Probably in the best of all cases 3, because if one country or one experiment sees a positive result, you're immediately going to want to confirm that because the science is so important. And you want to do it in a timely way, not have to wait 2 decades to get the answer. And so likely there needs to be at least 2, but they're so complex and so require so much resources that one region probably can't do more than 1. And so that again begs for international collaboration in order to make that science really be productive on a timely way.
Okay, thanks very much. We really should move on. Who will be giving us status on the IC design.
Okay, thank you for giving this opportunity to present the design of NEIC. I will give a brief update on the current status of the project. This is the outline of my talk. I will highlight very briefly the science at NEIC, and then in the rest of my talk I will focus on technical aspects of the design, such as design strategies. I will go over the individual components of the accelerator complex, collider complex, and I will also highlight some of the important aspects of the design. So to put things a little bit into perspective, here is the short-term timeline. The design has been evolving for over a decade. The physics case and machine requirements have been defined in the NEIC community's white paper in 2011, and then JLab produced a preliminary conceptual design report in 2012. Since then, every year we have regular internal reviews and continue design optimization. And as you heard, currently there is a long-range process going on. In January of this year, there has been a cost review where our design has been presented, and the results of this cost review, they fed into the long-range process. Our short-term goals is to finalize the baseline within the next few months, and then plan and execute pre-project R&D items, the most critical R&D. And then in the next couple of years, plan and execute the conceptual design report. And the overarching goal is to be ready for a CD1 and down selection. This is the an electron ion collider was recognized in 2007 NSAC's long-range plan as the machine, as the future machine for the study of QCD frontier. And it was stated that it will provide unique capabilities for the study of QCD, well beyond those available at the existing facilities. This is the white paper by the IC community that I mentioned earlier that identified the requirements of the electron ion collider. So I'm probably preaching to the choir by presenting the science highlights. And about it on the previous talk, but let me just say that the idea of EIC science is to study the sequence and gluon laminated matter in this region. It's nuclear imaging, spin structure, gluon dynamics. And from machine point of view, these studies require high luminosity, high polarization, and good detector acceptance. So why would we like to build an EIC Jefferson lab? First, there is a wide, well-established user community in the field. We have CBAF, which will serve as a full energy injector. The collider complex, in a sense, will be designed from scratch, but that's a good thing because it can be tailored to meet the experimental needs. With a broad central mass energy range, wide range of ion species, full acceptance detectors, high luminosity, and high polarization. And we are also intentionally trying to keep the technical risks low. Our design is based primarily on conventional technologies. Here is the layout of the MEIC on the Jefferson campus. So some of the basic parameters of MEIC at Jefferson Lab. The center of mass energy from 15 to 65 GeV, which translates into 3 to 10 GeV, electron energy and 20 to 100 GeV, proton energy, polarized light ions up to possibly lithium, and unpolarized light to heavy ions, up to 2 detectors, with the primary detector being a full acceptance detector. Luminosity in the range of 10 to the 33 to 10 to the 34 in this central mass range. Highly polarized electron and light ion beams, with electron polarization being longitudinal at the interaction points, and ion polarization adjustable to both transverse and longitudinal directions. And we also retain the possibility of upgrading the collider complex to higher energies and higher luminosities. This is an overall layout of the collider complex. This is the existing CBAF. The beam from CBAF would be injected into a new electron collider ring. And as a cost-saving measure, we are using many of the FAB2. We plan to reuse many of the FAB2 components, such as magnets, vacuum chamber, RF. The ion complex is new. It consists of the ion linen, ion source, ion superconducting linen, a single booster, and an ion collider ring. And again, mostly as a cost-saving measure, the booster and the ion collider ring are designed using superferric magnets. So a little bit about our strategy for designing high luminosity. So being an electron-ion collider, MEIC is in between hadron and lepton collider worlds. And what you have in a traditional hadron collider, usually there is a small number of bunches, so low repetition frequency, small collision frequency, and it's made up for by having a large bunch charge with colliding bunches. That leads to a relatively long bunch length and a large beta star to avoid the hourglass effect. Lepton colliders take somewhat different approach, and we are following this philosophy in MEIC. So we use superconducting RF in order to produce short bunches with low bunch charge and high repetition rate, and that allows us to have a very small beta star, which, in combination with small emittances produced by synchrotron radiation in the electron ring and electron pooling in the ion ring, gives a high luminosity. And this strategy, for instance, at KKB already reached the luminosity above 10 to the 34. Another unique feature of MEIC is figure 8 design of the collider rings and of the booster for polarization. The idea of figure 8 is quite simple. The spin precession in one arc is exactly cancelled by the other arc. So this makes the number of spin precessions in one term equal to 0. And by itself, such a situation is not stable. However, it allows one to control the spin with small solenoids or small compact spin rotators. And it offers a number of advantages. For instance, preservation of the ion polarization during acceleration, ease of spin manipulation, polarization direction can be adjusted as needed at the interaction points and reversed as needed. It seems to be the only practical way to accommodate polarized deuterons, and it also has advantages for electron polarization by removing energy dependence on the spin slip. So you all, of course, know CBUF, and as you heard, it has an exciting science program, at least for the next decade. And MEIC construction and operation is in principle consistent with the fixed target program. So the electron beam for injection in the MEIC would be taken from the whole D side. So CBUF will provide highly polarized, good quality electron beam. This is the overall layout of the electron collider ring. The total circumference is about 2,200 meters. It fits nicely on JLab's campus. As I mentioned earlier, some of the capture components are reused. We limit the synchronous radiation power to 10 kilowatts per meter with a total power consumption of 10 megawatts, which lets us have up to 3 amps at energies up to 7 GeV. At higher energies, we turn the current down in order to hit the total power limits. So some of the main components of the electron collider ring include spin rotators. Polarization is vertical in the arcs in order to avoid spin diffusion, and then it's rotated to be longitudinal at the interaction point. There are some sections for nonlinear dynamics, chromatistic compensation, RF sections, sections for control of the phase advance, the collider ring. In the baseline, there is a single interaction point with which is integrated into the collider ring with forward protection and space reserved for a second interaction point in the future. So now let me switch to the ion complex of MEIC. The ion sources of polarized and unpolarized light and periions are fairly conventional. The first acceleration was done by a superconducting linac with a warm front end. The linac design is based on Argon design of their version of free phase. It allows to reach proton energies of up to 285 MeV and heavy ion energies of up to 100 MeV per nucleon. One of the advantages of a superconducting linac is that it's universal and it can accelerate any ion species. The total length is about 120 meters. This is the booster, which accumulates, pulls, accelerates, and transfers ions into the ion collider ring. It's 273 meters long, also built using superconducting superferric magnets and shaped as a figure 8 for polarization preservation. Here's the ion collider ring. It is designed to match the geometry of the electron collider ring, of course, so that both rings are housed in the same tunnel. This is done by shaping the ends of the ion collider ring, and also these sections are used for dispersion suppression. The ion collider ring is designed also using superferric magnets, which operate at up to 3 Tesla, allowing for proton momentum of 100 GeV and operate at 4.2, 4.5 Kelvin. Their superferric magnet is essentially like a warm magnet, but with superconducting current leads and with iron going into saturation to some extent, so that requires what calls for special design. But they are significantly cheaper than conventional cosine superconducting magnets. And they're also cheaper to operate from some experience at GSI in Russia. So some of the other components of the INC library are RF section, electron cooling section, I'll talk about that later, tune trombone for phase advance control, interaction point with forward detection, and space for a second future ID. The central piece of the collider complex is, of course, the detector region. It has been designed in close collaboration between the detector designers and accelerator designers. The electron and ion beams cross at the interaction point at a 50 milliradian crossing angle, which has certain advantages for spin dynamics and for detector efficiencies also. Kinematically, most of the reaction products are boosted in the forward ion direction. So this requires careful design of the forward detection system. So the detection is done in 3 stages in the end cap, then using the small dipole covering angles up to here. So the first stage of detection is 2 meter long. Hello? The first stage of detection is a 2 meter end cap, then particles down to a few degrees scattering angles detected using this spectrometer dipole. And finally particles with angles below about 1 degree pass through the apertures of the final focusing quadrupoles and through another spectrometer dipole for further detection. On the electron side, things are all organized in a similar way. We have done a careful simulation of the detector performance and in particular of the far forward detection performance. And some of the highlights of the performance are neutrals can be detected in a cone of 25 milliradians. So here's a neutron track. The neutrals end up on one side of all beams with sufficient separation so that they can be detected with the ZTC. Particles fragments with momentum offsets down to 0.5% can be detected for all scattering angles, and all momentum can be detected down to at least 2 or 3 milliradians. One of the important components of MEAC is electron cooling. It is necessary for achieving high luminosity. And in MEAC, it's done in 2 stages. First, the conventional DC electron cooling is used in the booster to accumulate positive ions and reduce their emittance. Then, after the ions are transferred to the collider, there is another so-called bunched cooler, which is used to maintain emittance during stacking, and also to maintain emittance during collisions. So while DC cooler is conventional, bunch beam cooling has not been done before. For one thing, cooling efficiency drops down as a factor of gamma squared, and another thing is that required electron energies are up to 55 eV, which means they cannot be electrostatically accelerated, of course, with those energies. Some sort of RF accelerating structure is needed. So what the scheme proposed for bunch electron cooling is using NSRF limit to accelerate bunches to final energy. Then the bunch passes once through the ion beam, pulls it, then it's extracted, and in order to keep the energy consumption at the minimum, it's energy recovered and dumped. So this is a conceptually new technology which needs to be tested, but simulations are encouraging. Let me say a few words about the details of ion polarization scheme. In a conventional racetrack grid, say at 9 GeV, such as our booster, one would have to use Siberian snakes with field integrals of 30 decimeters for protons or about 100 decimeters for neutrons. In figure 8, polarization of any particle species can be preserved using a small solenoid with a field integral of only 0.7 Tesla meters. So that's the advantage of figure 8 design. In the collidering, the design is a little bit more complicated because the requirement now is not only to preserve the polarization, but also to be able to control its orientation at the interaction point. But it is done also using small 3 Tesla type solenoids and small dipoles. And these elements are weak enough that they have essentially no effect on the orbital dynamics. It can be easily integrated into the collidering, and they can provide any orientation of the polarization at IP, any in 3D space. Concerning electron polarization, I would like to highlight that polarization is vertical in arcs, then it's rotated in longitudinal direction in the straights, as I mentioned earlier, and that allows for sufficiently long polarization lifetimes of tens of hours at low energies and of the order of an hour at the top energy. So the beam can be quickly replaced as needed. And also downstream of the interaction point, there is a chicane with a Compton polarimeter which provides continuous non-invasive measurement of the polarization. So with these parameters and these components, the performance, the collider luminosity is shown here. It is above 10 to the 33 in the whole energy range for a full acceptance detector. And for a high luminosity detector, which has a little bit less detector space, it even reaches above 10 to the 34. So there is still a lot of work that needs to be done in the next 2 years. This is an overview of the R&D. We will, in the next 2 years, be building prototypes of superferric magnets and of some of the RF components. And we still have a lot of work to do on basically cost optimization, cost engineering, studies of nonlinear dynamics, electron cooling, ion polarization. So in summary, I would like to say that MEIC is a mature project. It's a ring-ring collider with luminosities in the range from 10 to the 33 to 10 to the 34 in a broad central mass energy range. Beam polarizations are expected to be very high, over 70%. It has low technical risk. It meets all the nuclear physics community requirements specified in the white paper. We still continue the R&D work and cost and performance optimization. And we foresee future operating energy at the university. Thank you.
We have some time for some questions. I had one question, which was a couple slides ago you were showing the, yeah, here. I assume that the energies of the 2 rings are completely independent?
Right.
I mean, you have sort of a loose correlation between the electron and proton energies, but presumably they could be any common.
Yes, we are not building in any correlation between the energies. I think it's a matter of kinematics and what we can accept.
Are there any other questions?
get to do the good stuff. Good morning, I'm Jerry Dreyer, President and CEO of Sura, who along with PAE Applied Technologies are partners in JSA. JSA is the contractor that to DOE for the management and operation of this laboratory. I'm very pleased to be here this morning and to present several awards that are made possible under the JSA Initiatives Fund. I'm also pleased to be here because after Tim's summary of the exciting stuff that's going on in nuclear physics, I'm sitting there wishing I was 40 years younger and heading out the gate. This is an exciting time for our field. It really is. I've been at it a long time, and to see it come to where it is right now is truly, truly exciting. So I'm jealous, but I'm also delighted at the same time. The Initiatives Fund program is a significant community building initiative with individual programs and projects that address broader impacts that JSA is making through a number of activities. Certainly promotion of education, teaching, training, learning, encouragement of broader participation of underrepresented minorities, and outreach to the science and research community, and in particular, and the focus of today, is awards to the user community itself. The Initiatives Fund program was started in 2006 with the onset of the current contract with DOE. Sura and PAE, our partner, and JSA have provided to date $4.25 million in support of initiative activities, making possible to date over 230 awards of one type or another. There has been typically within the program a one-to-one matching, and often more than one-to-one matching. So that multiplying factor brings the number up to extremely respectable. And I'm delighted to announce that with my PAE partner, Carl Williams, we have just signed off on continuing that contribution into next year at the 400K level. This morning, we will be honoring a number of recipients of prizes and awards sponsored under the Initiatives Fund program. So we're going to go through these systematically, and I'll be asking Bob, Mont, and others to join us up here as we hand over checks. I'll hand over the check. We'll let them take the picture, and we'll have a good time. The first one I want to look at, do I have to advance this? Yes. Is the Outstanding Nuclear Physicist Award. It recognizes individuals who have made outstanding and sustained contributions and are significant technical achievements in experimental and or theoretical research related to nuclear physics at Jefferson Lab. The selection panel, we thank them for their work, this year was chaired by Bob McEwen and included Science Council members, JSA Science Council members James Simons, JSA Programs Committee Chair John Hardy, and the 2013 Outstanding Nuclear Physicist recipient Doug Beck. The panel selected from among a number of strong nominees, two theorists this year. They're being recognized for their seminal work in the development of generalized parton distributions and the identification of associated experimental observables in deep inelastic competence scattering. That's thing about G and Anatoly Raniuska. Sendong is not with us today, but it's my understanding that totally he is. Sure he is. Come on down. usually don't hear the JSA in his title, but he's the president of JSA, as well as lab director Hugh Montgomery and deputy director Bob McEwen to come down and join me presenting these awards. Lest you think these things just happen, accidents, I'm going to go through a bit of the history of both of these gentlemen, so you gain appreciation, at least those of you who are younger, that it's a process to get to this level. So, in the case of Zeng Dong, he's a professor of theoretical physics now at the University of Maryland, and also serves as the director, Institute for Nuclear and Particle Physics in Shanghai University. That's where he is now, I understand, where he leads the Pan and X experiment. He's held postdoc positions at Caltech, as well as MIT, and was on the MIT faculty before joining the University of Maryland, College Park in 1996. He is a fellow of the American Physical Society. Previous awards include the 2014 Alexander Van Humboldt Foundation Research Award, 2010 National 1000 Talent Expert Award from China, 2003 recipient of the Outstanding Overseas Young Chinese Scientist Award from the National Science Foundation of China. Last place here. He's also a chair of theoretical physics at Peking University. So it's been a process at each point in his way here as he moves on. In the case of Anatoly, he's a professor at Old Dominion here, not just down the road a ways. He's senior staff scientist at Jefferson Lab as well, joint appointment. Prior to joining the lab at ODU in 1992, Anatoly was a scientist at the Laboratory for Theoretical Physics at the Joint Institute for Nuclear Research in Dubna since 1978, is that correct? He's a fellow of the American Physical Society as well. In addition to the Dubna Award in theoretical, he had Dubna Awards in theoretical physics in 79, 2003, 2010, and has won, well here, several awards from ODU University. Anatoly was also named the Virginia Outstanding Scientist of the Year in 2004, and was recipient of the Alexander Van Humboldt Fellowship Research Foundation Fellowship in 2001. So, congratulations again. Elizabeth, money first. This is important. Is it? It is an award for $5,000. It's actually 10. It's split between the two recipients. Congratulations. Next, it's the JSA Postdoctoral Research Prize. This award, which is for $10,000, was established 8 years ago by the user group as a way to recognize, reward, and honor the finest postdocs and support the lab's scientific mission. Over the years, the prize has helped to encourage students to see that excellence is recognized at every level, not just while you're doing your dissertation, but post graduation as well, and in the early career building phase of your careers. Of the past 7 prizes, 3 were awarded to JLab scientists. One, Patricia Savion, this year, just received DOE as Office of Science Early Career Research Grant too. So quality is there all the way. Patricia, congratulations. Are you here? No. Okay. This year, the user group board selected JLab theory postdoc Raul Racino. Raul, yeah. Come on down, please. Whoops, sorry. For his proposal, exotic mesons, resonances, and transition rates from quantum chromodynamics. I would like the user group chair, John, to come down and join us for this one, along with Bob and Mont. Raul has been a postdoc here at the lab since 2013, after receiving his PhD from the University of Washington. His dissertation was on the determination of elastic and inelastic nuclear observables from lattice QCD. Since joining the lab, Raul has helped to organize the Theory Center seminars, the Lattice QCD Journal Club. He's a guest lecturer at William and Mary, and he has a Hudson instructorship last year. So, congratulations on being this year's postdoctoral research recipient. Congratulations. Thank you. Moving on. The JSA Thesis Prize. The Thesis Prize was established in 1999 by the user group, then funded under SURA, and it's continued under JSA. It's an opportunity to recognize some of the best theses on Jefferson Lab science and research by graduate students. This award helps to launch their early career paths. Proud to be part of it. This year's user group board selected 2 recipients, Adesh Sudashi, is that it? Subedi, I'm sorry about that. My eyes are blurry, I've been pushing pretty hard lately. And Cristino Finelli. Are they both here? Would you both come down, please? Cristiano. Ashley is a graduate student at Michigan State University, Mississippi State, pardon me. It's right in my notes. Those two are easy to get mixed up. They're the same initials. So, and gave a talk on his thesis project yesterday, I believe. He's a postdoc now at Indiana University. Congratulations to you. Cristiano received his PhD from IFN in Rome. He gave his talk on his thesis yesterday as well. So congratulations to you. Elizabeth, we have a plaque and a check for $1,250 for each. Gentlemen, would you come forward? This one. this completes the formal awards and presentations for the morning. There are a number of other things that we have done. I'm not going to go through the details, but I do want to let you know that this isn't all of it. There's much more. And you can see other JSA prizes and awards. The poster prizes, I understand that those were awarded on Monday. And there are other prizes that have been awarded. Graduate fellowships, as well as sabbaticals. So we are out there, while we may be the contractor and responsible for making sure the lab behaves itself in an appropriate business-like fashion, we are also very attuned and attentive to the science and to promoting the science in every way possible. So, let me take this opportunity to flash it for you a couple other things that we do. It is, the initiative's fund is a community building activity. I step over here so I can see. You can see we support ILCAC, the International Light Cohen Advisory Committee. They are actually an organization established under CERA. We also have established under us the National Society of Hispanic Physicists. Last year we won an award from Virginia Center for Innovative Technology. This is Drew Weisenberger, next generation work on the Dillon camera. That support ran through CERA. And over on the right, the Cygnus is an NSHP award from the NSF for advancing their program, and in particular their annual meeting. So you see that we've got our fingerprints on a number of things that are ongoing in the arena of broader impacts. And although we don't tout this in a big way, Tim will appreciate how important it is to the field of nuclear physics, to science in general, but to the field of nuclear physics in particular, and to this lab also. So within that framework, we have a vigorous relations program that we participate in. And John, we're particularly pleased this year because of the good showing of the Jefferson Lab contingent when we had a Hill Day. I think we outnumbered, I can brag a little bit, can't I? We outnumbered FRIP this year, too short of Brookhaven, but we're moving up and into a strong leadership role as we talk to those who provide and approve funding for nuclear physics program in general and for our individual projects as well under that. So that concludes our program for the day. Just a personal word. I am a nuclear theorist, and like I said, 40 years erased from your life and start again. This is an exciting time. It really is. Tim, you'll appreciate it. You know, no problem there with age. And Mont and Bob, I know I speak on behalf of all of you, how great it is to see the upswell of excitement within our community for the science that we're looking at and looking for as we move forward. So it's a pleasure always to be here to join you, to add to the program through these celebrations and awards, but also just to give you general encouragement for how well I think this lab is doing, you as individual researchers, and the user group here. It's great. We appreciate it. Push on. Thank you very much.
That concludes the session for this morning, and so the session reconvenes at 11 o'clock.
session is by Mark Dahl, who's going to talk about the Q-week experiment.
Thank you. Anyway, thank you for this opportunity to talk about some new data from the Q-week experiment and also a rather interesting new possibility for measuring the elastic form factors of the delta. I think the last speaker must still have a clicker. Oh, there it is. Okay. So we're trying to understand more about quantum chromodynamics. It's responsible for most of the visible mass in the universe. It has some very interesting features. Arguably the most interesting is this gluon-gluon self interaction, which leads it to be very weak at high energies, but very strong at low energies, which are appropriate for the matter that we see around us. And so the question that we have to ask ourselves is, how do we study the strong coupling regime of QCD? So there's a number of potential ways you can do this. One of them is spectroscopy, so you can study the properties of the states of QCD, so their production mechanisms, their mass, their width, quantum numbers, and decay modes. And this has been a pretty successful, fruitful endeavor over the years, and in fact the quark model itself grew out of such studies. You can study also form factors, so they contain various kinds of information, including the positions of charges within a hadron. But studying elastic form factors, you run out of targets very quickly. You can study the proton, the neutron. If you're very careful, you can study the pion, and that's pretty much it. So today I'm going to tell you about a method that might allow us to access the elastic form factors of the delta itself. And so the delta is this lowest lying nucleon excitation, which is experimentally well separated from non-resonant and other resonant contributions. That unfortunately is very short-lived, and this is the problem. That's why you can't study the elastic properties of the delta. Okay, but just to introduce these elastic properties of the delta, so the delta is a spin 3-half object. That means it has 4 form factors. So it has this charge and magnetization form factor, a quadrupole form factor, and an octupole form factor. And these are associated with the distribution of charge and magnetization in the object, in the delta, and also non-spherical deformations. So if you then look at these form factors at the limit where you don't transfer any momentum to the delta, then the charge form factor is just the charge of the delta. The magnetic form factor is becomes the magnetic moment, and you have the dipole moment, sorry, that should be quadrupole moment, sorry, quadrupole moment, and octupole moment for the delta. So this is the kind of thing that we'd like to study if we had a stable delta. So what do we know about these form factors? Well, there is a measurement of the magnetic moment of the delta. This is a very interesting measurement where the delta is essentially decays to itself, emits a photon, and it remains a resonance, and then emits a pi zero. Very nice measurement. But other than that, there's really no direct measurements of these properties. You can learn something about the elastic properties by studying the transition properties from a proton to a delta, for example. But these are always model-dependent extractions. Okay, so now I just want to introduce to you this technique, which we call beam normal single spin asymmetry. So basically, if you polarize an electron perpendicular to its direction of motion and you scatter it off a proton or a nucleus, then you will notice that you get more scattering to the left side than you do to the right side if your electron is polarized up. And if it's polarized down, then you get the reverse. So what we do in experiment is we reverse these polarizations and we apply an asymmetry. Okay, so now this asymmetry due to time reversal invariance arguments, it vanishes for one photon exchange. So this is something that only occurs in 2 or more photon exchange. And in fact, to leading order, it's the interference between one photon exchange amplitude and the imaginary part of the 2 photon exchange amplitude that contributes. So what we're measuring is the difference between the 2 polarization states over the sum, and this is related to the imaginary part of the 2 photon exchange amplitude interfering with the 1 photon exchange amplitude. The symmetry is very small, so because it's a 2 photon process, it's got an order of alpha in there, and because you have an ultra-relativistic object, the electron polarized perpendicular to its direction of motion, you have this suppression of the mass over the energy. So we're looking at part per million level asymmetries. Now the calculation itself, if you want to do this interference, so the fact that the imaginary part is quite useful. That means you can cut the diagram in half, and in fact all the states along this line are on shell. All these hadronic states are actually on shell, which is quite useful. Okay, so 2 photon exchange processes have been very interesting over the last decade. This is the example where you have the same process and you look at elastic scattering of the proton. So what was it learned very early on is that you can't describe this process if you only have the proton in the intermediate state. Then you get these dotted lines over here. You get a very essentially negligible asymmetry. So you need to include intermediate states into this calculation over there so that you can reproduce the data. And then if you do that, you reproduce the data pretty well. And in fact, most of the disagreement between data and calculations is supposed to be due to the fact that not all intermediate states are included. So this is only the single pion intermediate states that are included in these calculations. So you can do the same thing, measure the beam normal single spin asymmetry of nuclei, and once again, things are pretty much under control. So here we have atomic number versus asymmetry for the proton, for helium, and for carbon. Calculations do a very good job of explaining the data. There is this anomaly, so scattering of lead 208 gives an asymmetry that's basically 0, as near as we've measured it, but this is assumed to be due to Coulomb distortions, and there are data that might help to understand this. So Curie is sitting on some data that's being analyzed right now, and up to aluminum 27, and then the C-Rex experiments should take similar data for calcium and might shed some light on this discrepancy. But the message is that essentially over a broad range of data, the calculations do a good job of describing it if they include intermediate states. Okay, so now let's look at how you might do such a calculation for the delta process, where you measure the beam normal single spin asymmetry for a delta production. So in that case, it's a little different. You have the nucleon on one side and you produce the delta on the other side. This is the single photon exchange diagram. But then you have 2 photon exchange and the intermediate states. So in one case, you might have the nucleon in the intermediate state. You might also have a delta in the intermediate state, and you could potentially have many other states in the intermediate state. So let's tackle these vertices one by one. This vertex here is just the nucleon form factor. That's pretty well known. This vertex here is the nucleon to delta transition form factor, and that's also been measured to adequate accuracy for these purposes. Here again, this is the nucleon to delta transition form factor, and again, this is the nucleon to delta transition form factor. And here is the part that we are interested in. This is the delta form factor, so you can see that we have a delta in the intermediate state, it scatters off a photon, and delta in the exit state. So that's the elastic form factor, and that's what we're interested in probing. And then we have this, which is the theoretical background, essentially, which is difficult to calculate, and I'll mention a little bit more about that later. So, one thing to note about this is that the energy of the invariant mass of the hadronic states that can occur in the intermediate state is directly related to the beam energy. So here's plotted beam energy on the x-axis, and here is this invariant mass on the y-axis. So you can see that as you go up in energy, you start to unlock more and more and more intermediate states that can occur in this diagram. So if you're interested in studying this vertex without having all of this other stuff, you want to be coming down and down in beam energy as much as you can. These black lines represent the width of the delta. So how might you start doing calculations for this delta form factor? Well, you can just go to the lattice. So in this case, there's a lattice calculation from 2009. They've used various pi masses down to pi masses of 350 MeV. So at these pi masses, the delta is still stable. You wouldn't want to go lower than these pi masses in this formalism because it's not really set up to handle the decay of the delta. But in any case, the calculations tend to be relatively stable with decreasing pi mass. And what they've done is they've fitted some phenomenological model of the delta form factor to these lattice calculations, and it's a reasonably good fit. So this is for the case of the electric and magnetic form factors, and this is for the case of the quadrupole form factor. So in this case, if you do, there are some disagreements. There's a very small signal. You can see that much larger uncertainties, and in fact, for the octopole case, the lattice calculation here wasn't able to extract a signal that's consistent with zero. Okay, so we can just push on. We can use these extracted fits to the lattice calculations. This is the form that they used in that paper. The electric form factor has a dipole dependence, and the magnetic and quadrupole form factors, they're falling faster than a dipole. They have another parameter, and the octopole is just set to zero. But you could consider alternative ways of parameterizing these form factors. So, for example, you could parameterize it so that the charge radius of the delta is more obviously a parameter. So, you know, in this climate where people are now relatively concerned about the sizes of nuclear objects like the proton, it might be very interesting to try and extract the charge radius from the delta. But really, what's important, I guess, is how sensitive are the calculations of the asymmetry to changes in the parameterization of these form factors and changes in the parameters such as the radius, magnetic moment, protocol moment, etc. So if it turns out that the calculations are very sensitive to those things, then we have a hope of extracting this information from a measurement of the asymmetry. So I will show some preliminary calculations in a moment. Just to get back to the dependence on the beam energy, I mentioned this already, and this is an example from the elastic scattering case. So if you have a beam of 850 GeV, and you take into account all the intermediate states, then you can see here, for example, the contributions of all the intermediate states to the asymmetry, and you see that you have to include non-resonant and higher resonances. If you raise your beam energy to 3 GeV, then you have to include a lot more states, including well into the non-resonant region if these start to get large. So just an argument for keeping the beam energy low. Okay, so here's some calculations for the asymmetry of the delta. And what's been included here is the proton intermediate state and the delta intermediate state. So none of the other higher order states are yet included. And what you can see, if you look carefully, is that at forward angles, so this is the, these are the angles at which the QE kinematics occurs at this beam energy, and I'll show the QE data here. You can see that the contribution from the delta intermediate state and the proton intermediate state are approximately equal. As you go more towards backwards angles, the delta intermediate state becomes much larger, becomes the dominant contribution. Okay, so that's interesting. So now you ask, what are the sensitivities to the form factor? The most basic way to see how sensitive you are to the form factor is to just turn it off. So here, one by one, the electric, magnetic, and quadrupole form factors are set to 0, and we have a look at what the effect is. So if you set the electric form factor to 0, basically the contribution from the delta intermediate state at forward angles just disappears. So at forward angles, you're almost completely sensitive to the electric form factor. At backward angles, if you set the magnetic form factor to 0, then the contribution from the delta intermediate state basically disappears. So at backward angles, you're essentially completely sensitive to the magnetic form factor. Setting the quadrupole form factor to 0, unfortunately, it's hard to see. It basically doesn't make a difference. So unless you have a very precise measurement, it's unlikely this technique will be sensitive to the quadrupole form factor. So having introduced the calculations, the measurement that I'm about to present is done using the QE apparatus. So it's designed to measure very small asymmetry down to 10 parts per billion on the order on the final extraction of the weak charge of the proton. And what the experiment has to do is measure the transverse polarization asymmetry and inelastic asymmetries for background studies. We spend some very small fraction of the time doing this to constrain how the backgrounds might contribute to the main measurement. This is a picture of the apparatus with the shielding cutaway. We have this toroidal spectrometer. We have this collimation, and then these beam envelopes of electrons travel towards our integrating Cherenkov quartz detectors. So what we have is this, these 8 detectors which are in a circle, essentially, and that's very useful for looking at azimuthal asymmetries, and this evenal asymmetries and azimuthal asymmetry. So the one major issue with this data set is that because we have a very thick target, it's 35 centimeters long, and we also have very forward kinematics, we get a significant contribution under the delta peak from radiated elastic scattering. So this you can tell in this plot over here. So the red is the elastic scattering rate, and the blue is the delta rate. So in fact, the delta rate is approximately only 30% of the total integrated asymmetry that we measure at some lower magnetic field. So the knowledge of the asymmetry is dominated, of the underlying delta asymmetry then is dominated by the knowledge of the relative fractions of the elastic and delta production. And so you can see here, the reason that happens, the delta has a large asymmetry and low rate, the proton has a small asymmetry and high rate, and then somewhere you get this cancellation between the two. They have the asymmetries of opposite sign. And so then knowledge of the individual rates becomes very important. So there's quite a lot of work being done at the moment to do a very sophisticated treatment of radiative effects, and this is following the Dasu and Tsai numerical integral technique that was used in Dasu's thesis. So these are the measurements. So the proton elastic asymmetry has already been measured to quite high precision, and a preliminary number has been published in a conference proceedings. Then we also have this measurement at the delta peak, which is opposite in sign, but approximately the same magnitude as the measurement for the elastic case. So now we just have to do some algebra and extract what the actual delta asymmetry must be. That's what's plotted here. So here's the calculation from Pasquini. So the two intermediate states that she considers the delta and the nucleon, there's some compared to the QE measurement. So at the moment, the measurement is at a level where we can essentially confirm that the calculations are on the right track, but not really precise enough to test individual models of the delta elastic form factor. However, we expect a significant decrease in the uncertainty as these radiative effects are understood. We have similar data available at a lower beam energy, which should help with interpreting the results and also help in understanding contributions from from the higher order intermediate states. And there's also more data available at this beam energy with different background fractions, which should really help us in disentangling the true contribution from the elastic background. Okay, so there are other places you can do this kind of work. Mainz, as a byproduct of their parity violation program, has data at the delta. They detect slightly differently. They have a calorimeter, and they distinguish elastic from inelastic events by the energy deposited as their elastic peak, and you can see there's the delta contribution. So they expect to be able to extract similar data. In their case, they'll have a larger scattering angle, and they'll have two beam energies where they're fairly confident of extracting these asymmetries with fairly small uncertainties, which is nice. They also have potential data at lower beam energies. However, there's a concern: the lower you go in beam energy, the lower your scattered electron energy is, and it makes detection difficult. So they're going to have a look and see how well they can analyze this data and extract an asymmetry. It might not be possible. They also have backward angle data, which would be very interesting because that's more sensitive to the magnetic form factor. But once again, they're concerned about the low energies of the scattering data. So there's this workshop going to happen next month at Cornell, and they're interested in looking at what kinds of physics can be done with intense electron beams. So search for dark photons, parity violation, all this kind of stuff. And there's various different facilities that you might consider doing a future measurement of this observable A1 at Mainz, at the Cornell Accelerator, at JLab's low energy recirculating facility, or solid at JLab. So let me just mention solid for a little bit. It has these scattering angles, so you probe the electric part of the form factor. It has a very high rate capability, so if you have this spectrometer built to study parity violation, you would need less than a day of beam time to measure this particular observable. The figure of merit goes down with scattering rate. The scattering rate, the asymmetry, and the interpretability all go up as the beam energy goes lower. Something to stress. So here's a summary of the measurements. QE is the magenta here. We have these two beam energies that we will publish either this year or early next year. Mainz has, in the blue, has two beam energies that they hope to release this year or early next year. And then potential Mainz data at lower, much lower beam energies. We can only hope. Solid has the nominal beam energy at 2.2 GeV, although in principle you could set CLab to run at any of these energies. Okay, so in summary, this observable, the beam normal single spin asymmetry in delta production, is sensitive to the delta elastic form factors. Measurement of these asymmetries is a mature, robust technique. These asymmetries might allow for experimental testing of the elastic form factor calculations, but more theoretical studies are needed to determine how well that can really work. And certainly future missions might be possible. Thank you.
Thank you for a very nice talk. Are there any questions?
Yes.
So you made an explicit statement that the intermediate states are on-shell. However, they're off-shell. Because in principle, if you sit on the delta resonance and you want to calculate that the neutron, there's a part from the neutron and a part from the delta, it already tells you that the intermediate states can be off-shell. And this is partly the problem with some of these calculations, because in reality, that the intermediate state can be any excited state. And the further you are away from your W, the further off-shell they are. The only what the theorists do is they calculate it on shell, because that's why we have experimental knowledge. But in principle, these intermediate states are off-shell, they're not on-shell. And the fact that a neutron has a contribution, even though you're sitting on top of the W resonance, proves the point directly. They're off-shell. And the calculations are done on-shell, because all we know is on-shell form factors and just like that. So the theorists will do that. But in principle, you could put in the neutron, the delta, the S11, whatever you want in the intermediate state. And the fact is, more or less, because you're at a certain W, you get further and further away from the energy of those states. So there's somewhere 1 over energy minus W contribution, so the contribution gets less and less and less. So they're offshore.
Well, I mean, of course, I don't want to get into an argument. I'm not sure we're maybe talking about the same thing. So in the real part of the two-photon exchange, certainly that's off-shell. Right? So it's the stuff that contributes to the proton form factor. So I mean, maybe a theorist would like to back me up here, or I mean, it's kind of like a more of a philosophical thing, perhaps. But when you know, so if you say, I mean, it's hard for me to address that, right? I've never heard any theorist disagree with these statements.
Any other questions? I had one related to your one measurement that you had shown. I was wondering for the error you showed, is that just the discipline uncertainty here or the systematic uncertainty?
Which one?
I believe it was on slide 17.
This here?
That one there.
So that's only systematics, essentially. The statistics are tiny by comparison. So it's really asking, you know, how well do we know relative fractions of all the contributions. I mean, I spoke only about the elastic and the delta, but it's really about the contribution. You know, if we get the systematics under control, it's going to become a lot smaller.
Any other questions? If not, then let's thank our speaker again. Our second speaker for the session is Whitney Armstrong. He's going to talk about the measurement of the spinning symmetries for the political resistance.
All right, can you hear me? Is this on? It is? Okay, good. So yeah, I'm going to talk about the same experiment. Here's an outline of my talk. First, I'm going to give motivation, which may take some time, and then I'm going to try to go as quickly as I can over the same experiment apparatus itself, and then talk about the analysis, and then present some results, preliminary results that we have. So first, the motivation, this slide is very similar to Mark's first slide, actually. So we're going to have the running intercoupling. So you have QCD. It's not the constituent quarks that are the degrees of freedom in the Lagrangians. It's the current quarks. And QCD has been very successful. It's made many predictions. from PQCD at high energies. And QCD is believed to be the correct theory of strong force. QCD should be able to describe the structure of the proton and the neutron. However, because of perturbative techniques cannot be used to describe the complex balanced state of quark and gluon fields, which make up the nucleon, we have to resort to some other techniques. So what does the nucleon look like? So at large scales, you have a pion cloud. It doesn't tell you much about the QCD. You start going at smaller and smaller scales, and you start resolving more and more quarks and gluons. Everybody I'm sure is familiar with this. But the point here is that we're going to use our understanding of PQCD at high energies, at high Q squared, to begin to test our understanding at lower Q squared. And the main tool for doing this is the operator product expansion. So I'm sure, again, everybody's familiar with deep inelastic scattering. You have the Bjorken X variable and the form momentum transfer squared, Q squared. And you can access the unpolarized structure functions F1 and F2. F1 is relating to the quark distributions in the standard way, and then in the Bjorken limit, you have this count-gross relation between F1 and F2. What I'm going to focus on and talk about is polarized deep inelastic scattering. Polarized deep inelastic scattering, you measure a double spin asymmetry. That is the asymmetry formed with a polarized electron and a polarized target. The target can be polarized both longitudinal to the electron beam and transverse to the electron beam. And with a longitudinally polarized target, you can see here from the formula for the asymmetry for parallel and perpendicular, you have access to G1 and G2. But for the parallel target, the G2 contribution is suppressed by 1 over nu. But if you go to a transversely polarized target, you see that in the transverse asymmetry, G1 and G2 contribute equally. And as I'll discuss further, G2 is directly sensitive to non-perturbative effects. So similar to F1, G1 has this relation to the polarized parton distributions, and G2 has no simple partonic interpretation. So if you go to the operator product expansion and you could derive an infinite set of sum rules for involving G1 and G2, and for the first case, for n equals to 3, you get this sum rule here where D2 is a reduced matrix element. There's two interpretations available for D2. One is color polarizabilities, and the second is the average color Lorentz force. So I'm going to focus on this second one due to Matthias Burkhardt. So if you look at the matrix element and consider the fact that you're in an infinite momentum frame, and look at the field strength, the gluon field strength tensor involved, you see that it decomposes into something that looks a lot like the Lorentz force. That is the transverse component of the Lorentz force. And Matthias offered this interpretation that D2 is the average color Lorentz force acting on the quark, which is moving backwards in the infinite momentum frame, instant after being struck by the virtual photon. So D2 allows you to measure an average color force, which is a very nice interpretation. So how do we get at D2 experimentally? We measure G2. And G2 has what's called the 1-0 Wilczek contribution, and then G2 bar, which is a pure twist 3 contribution. So looking at the leading twist, G2WW is written this way, and we call this G2 twist 2 or G2WW. The twist 3 piece, which connects quark-gluon correlations to G2, can be G2 bar can be written as this way, where this is a transversely where you have this quark mass term, and then this term here is a pure genuine twist 3 contribution. So G2 bar is sensitive to higher twists, specifically the next deleting is this twist 3. So D2 is written as this, as 3 times the x squared weighted integral of G2 bar, or you can write it like this, involving G1 and G2. Now, as the question that I find interesting and important to answer, at least here at Jefferson Lab, is as Q squared decreases, when do higher twists begin to matter? I don't know if anybody's ever answered this question by measurement. We know that higher twists matter at low Q squared, but we don't know exactly when they begin to really matter. So, okay, now I'm going to go on a little bit of a tangent here with orbital angular momentum, so if you can bear with me. So everybody knows this G relation for the orbital angular momentum of the quarks. There's also another relation involving this twist 3 GPD. So essentially what you have here is you have 2 equations, right, for the same quantity. Now the twist 3 GPD, big G2, decomposes similar to little g2, in that it has a leading twist part, a twist 2 part, and then a genuine twist 3 part. Now, from you can derive some rules analogous to what I've shown for the operator particle expansion slides earlier, and they, Kiptoli and Polyakov derive some rules, and here is one from this paper that they derived a whole bunch of samples. So you see here that it's equal to D2. Now if you plug in the definition of D2 from earlier here, you see that if you match the integrands, you can say that the twist 3 part of this, in the forward limit of this GPD, is equal to this. And it makes sense that you have a forward limit going to something that's related to DIS quantities, because you have the same thing in H tilde H. So it's not unreasonable to, I don't think it's unreasonable to draw this conclusion that this is equal to that. Similarly, there's a sum rule for G2WW in this paper, and if you go to the forward limit and match the integrands there, you arrive at this. So then, you have 2 equations for the same quantity. If you solve for, in this one, for x, h plus e, and substitute it into the second one, and then solve for LQ, you arrive at this relationship between this, I haven't seen this anywhere, so, and I could be wrong. So I'm just putting it out there to generate some discussion, but you arrive at a relationship between orbital angular momentum of the quark, HQ, which is essentially delta Q, and this genuine twist 3 part involving quark-gluon correlations. This has a nice feature in that the explicit spin orbit anti-correlation is shown by this minus sign here. And so there are some caveats and things I should note, though, is that extracting G2 bar for calculating this, you actually need the difference because of this x here. But if at high x, it's probably a good assumption that you can neglect the anti-quark distribution. So in measurements, inclusive DIS measurements, you can actually get at least the leading contribution, which is just the quark, because you're now looking mostly at the valence. And also, there's other caveats about the neglecting higher twist. So, this is a new relation. I don't think I've seen this anywhere, and it might be wrong. I don't know. I hope somebody did tell me that. But if you go even further and plug it into the 2 definitions, the G and then the Jeffrey-Monahar decomposition, do a little algebra, you find that you have this new relation between the 2 decompositions. You have the 2 pieces which now remain unmeasured, then everything on the right side of this equal sign you can measure, assuming that this is correct. So the missing link then in putting these two decompositions together, there's only one more relation that's needed really to sort of complete the picture between the two. That is something involving one of these to something else. So you can have another equation to solve for these two unknowns. Something that is interesting along the lines of D2 would be the fact that Burkhardt mentions this connection between the two descriptions as being the torque generating angular momentum as the struck quark is ejected from the nucleon. And I'm sure Matthias will talk about this, so see his talk later this afternoon. And so this could actually be the possible connection, but I'm not sure. So anyway, so tangent over. The status of the spin structure functions for intermediate Q squared is shown here for the experiments, but not showing any class data. If I show class data in this range, you see that it adds some points here, and then I throw some models on it, and you see that we need more high X data, and this is the X squared G1. That is the part of the G1 contribution to the D2 integrand. Next, if you look at X squared G2, similarly, this is the world data, and you can see here that it's at mostly low X. And if you put the G2WW models on top of that, you can see that there's strong variance. These data points here are kind of all over the place. So not only more high X data is needed, I say more data is needed. So here's the status of D2 for the proton on the left. Here's the integral, and then I put here as a caveat the knocking moment, which takes care of the target mass corrections, giving you target mass correction free D2. So here's the only measurement here from SLAC, and then the only other measurement is from RSS, which is at low Q squared here. There's just two measurements so far. The lattice QCD is able to calculate D2, and this was done a while ago, and its point is right here, and it's in agreement with the SLAC for the proton. But they were done a long time ago, and I believe they were in the Quench approximation, and they agree with the proton, and over here I show the neutron, the latest neutron results from Paul A, the D2N experiment. And you see here that the SLAC data points were in disagreement with lattice, which is here, but now with the Hall A measurement, they seem to agree with lattice calculation, which was done over a decade ago. So updated and improved lattice results are long overdue. So let me summarize real quickly what we can do with G2. Polarized DIS is uniquely poised to provide insight into quark-gluon correlations. Direct access to higher twists using a transversely polarized target. G2 bar is possibly connected to the quark orbital angular momentum in G2, obviously. Twist-free matrix element, D2P is proportional to an average Lorentz color force. Amish QCD calculations can be put to the test. And JLab provides the best opportunities to explore the valence region needed to make these measurements. So precision measurements of G1 and G2 at JLab provide great insight into non-perturbative structure of the nucleon and test our understanding of QCD. So now, since I'm running out of time, I'm going to quickly go through the same experiment. And here's a very old picture of JLab. I'm sure, I don't know when this was taken, but clearly it was a long time ago. So here's LC. Here are the spokespersons for the experiment. We measured two double spinning symmetries A180 and A80, where 180 refers to the launch anti-parallel target, and then 80 refers to the nearly transverse target. We used two beam energies, 4.7 and 5.9 GeV, polarized ammonia target, and we detected electrons primarily with this big electron telescope array, or beta. And here's an overview of the configuration of the hull. We have the target here, which we picked up and rotated for the two target configurations. There was a chicane for the transverse target running, and we had a helium bag installed on the beam dome. And over here at 40 degrees sat beta. Beta was unique in that it had covered a large solid angle and had a large momentum acceptance. It sat out in the open, and it wasn't behind a momentum selecting magnet. That is, the energy was only determined by the calibrometer. Here's a picture of it installed in the hull. Right here in the middle is the big cal. Over here is the gas Cherenkov, the T. And in front, behind this lead wall, is a photoscope, and then here's another lucite photoscope. So first, big cal is composed of two sections of lead glass. The upper part was from Yerevan. It consisted of slightly larger blocks. The lower part was from the Institute for Energy Physics in Oviedo, Russia, and it consisted of slightly smaller block sizes. And there was 1,744 lead glass blocks total. The gas Cherenkov tank used to identify the electrons had four spherical mirrors and four toroidal mirrors, and they focused the light, Cherenkov light, on the 3-inch quartz tubes, which were selected for their UV sensitivity. And here's actually a result of the gas Cherenkov so this is one PMT. You see here, this is the single track peak, so we have a large number of photoelectrons, about 20. And here's the second peak where you have now a pair going through. So by placing cut here and here, you can cleanly select the good one electron events if you're interested, and remove all of this background over here. Sitting just behind that, the Cherenkov was the lucite photoscope. The photoscope consists of 20 curved lucite bars, with PMTs at both ends, and it was used in coincidence for a timing coincidence to better eliminate the background. And then also up front we had a forward tracker, which consisted of scintillators and details you can see here. So we also used the UVA target group's polarized ammonia target. So here you can see the polarization as a function of run number, and it had a 5 Tesla magnetic field, and the average polarization was about 69%. So next, I'm going to talk about the data analysis real quick. So the reconstruction, primary reconstruction was done using neural networks. And we had two main networks and then a third. One was used to get the position at Big Cal, and then the second one was used to reconstruct through the magnetic field to get the target variables. And here you can see just a position, an example of the position reconstruction improvement, where the blue and the black are the input, and then the difference is the red. So it works quite nicely, and the inputs were mainly the various moments in X and Y, and they give you these this information. So next, the asymmetry and kinematics are shown here. So raw asymmetry is given as the difference over the sum, and we correct it for charge at lifetime. Here's for parallel and transverse target. This asymmetry then is corrected for beam and target polarization, as well as the target dilution for all the unpolarized material in the target. So the dilution factor was calculated, the dilution factor needs a main ingredient from about the target, and that is the packing fraction. It's how the ammonia beads settled in the target cup. And this was done by using HMS to calculate this ratio and model it in the simulations using this cross-section model. And it was determined to be roughly 60%, and this was some work done by Boyang, Narvi, and Anusha. with the packing fraction now, we can calculate the dilution factor on, and you can see that it's given here as the ratio of the polarized material to all material, and it's a function of the W and Q squared because the cross sections of course change with the given mass. Okay, so here I show some of the asymmetries. The left side are the parallel, on the right side are the perpendicular asymmetries. The upper ones are for 4.7 GeV energies, and the bottom two are for 5.9. So I should mention that there was a target magnet problem which we had, which delayed the running, and we were only actually able to get a little bit less than 50% of the data that was in the proposal. And this is really only thanks to the hard work of JLab staff, the Halsey staff, and all the target group and everybody. They came together and they fixed the magnet and scrambled to get it up and running, and we're actually able to take some data. And I want to say that without that hard effort, that this experiment otherwise would have never happened. So after with these asymmetries, we now have to correct for the background, and this is done by looking at the ratio of positrons to electrons. So the possible sources of backgrounds are limited and few, and there's pretty much one that dominates, and that is pi zero production. So you have a pi zero produced, it decays, photon produces a pair, and one of those electrons goes into the detector, and that's a background that we want to eliminate. So in order to do this, we initially used Weiser's Weiser model of the inclusive photo production data. We run the Monte Carlo, and then we also did a very nice fit to the available pion asymmetry data, so we can get an estimate of what could be the contamination from a pion asymmetry. And we get this formula here, and the dilution comes from simulation. And this actually is the focus of the remaining work that we have to do, is to really pin this down and get this right so we can go to lower X. So this is pretty much all the remaining work that we're doing. I've been working on fitting all the inclusive pion photo production and electrode production data I can find. So if you have any that you didn't publish from your experiments and are willing to share, please let me know. I'd be very interested in them. So, the Weiser fit is almost 40 years old and everybody's still using it, so I thought it was time to update this. Skip that. So then the next thing after the background corrections is to do the radiative corrections, which I'm sure everybody's familiar with. We rewrote some code to check some things. And pretty much the polarized formalism is nearly identical to the standard MoSi treatment. That's pretty much what we found. And so the radiative corrections that matter the most is the elastic tail subtraction. So over here you can see for parallel, for the various Q squared bits, what the dilution piece is, and then below you can see what the contamination piece is. That is, at low X you start to get the increasing elastic radiative tail coming in. So the thing to point out here is that it's really important in calculating this to also calculate the radiative tail for the inelastic cross section. So it matters in calculating this elastic radiative tail correction as well. So once you make all these corrections, you get similar asymmetries like this, and those aren't as interesting as showing some results for G1 and G2. So I'll skip ahead. So again, here's the world data. Now here's the same data. So this is before, and then this is after. You can see that at high X, we have a lot more data here. And down here at low X, you see this is where we're trying to pin down the systematics and get the background correction right. This is where it comes into most. But you can see over here, though, a significant increase in the data on G2. And if I overlay the models, you see that how things are looking. And over here, it's just G2 dumping better. Okay. Now that we have this G1 and G2, we can calculate D2. So again, here's the existing plot of earlier I forgot to mention there's various model predictions. And here's the slack point with the lattice point. So with the existing data, now I overlay the Nachman moments in blue here, these 4 points in blue, and then up here is the RSS. So this is a preliminary showing statistical errors only. The systematic errors aren't shown, so don't quote these numbers, but I just wanted to show some results. So the thing that's interesting here is that if you look here, we're in agreement with slack. We're also in agreement with the lattice point, despite its large errors. But as you go to lower Q squared, you see that this point down here is slightly lower. And what you would expect from the PQCD evolution of the twist 3 matrix element is that this would just sort of increase as lower Q squared, kind of like this curve is doing. And I should mention that this curve that you see here, the blue one, is just the elastic contribution because the integral goes to 1. So from the form factors, you can calculate the elastic contribution. So the net D2 is the elastic plus the inelastic, which is what we measure. So I add here the Cornwell-Norton moments, which are right here. This standard form, you see that the target mass corrections matter. And I have here this CN elastic curve as well, just to show you how things are looking. So if you look over here at the neutron data as well, they observe a dip off of the elastic too at about the same Q squared. And here's the blown up view, and I put the arrows there just to sort of highlight the difference. So is this a flavor independent average color force? Updated lattice calculations are long overdue. I know I've been told it's a very difficult problem to do, and it's very, takes a lot of time, and I think it was at least worth a graduate student spending their whole thesis on calculating this. So I want to just encourage that D2, encourage the lattice community to calculate D2. Because you can see the error bars are quite big. So, and they could do the Q squared evolution and not just one data point, they could do it and make a prediction, well, not a prediction anymore. So I'm going to conclude now. So the same results significantly improve world data on G2. D2 result seems to indicate a negative or 0 value around Q squared 3 to 6. A 1 standard deviation level consistent with the neutron result. That is, comparing to the neutron D2N, the average transverse color force appears flavor independent. And you might ask, is this surprising at all? Not really, because the flavor average color structure of the nucleon should be flavor independent. They're just isospheres. So a flavor decomposition of D2 would provide new insight into its flavor structure, and also G2 bar, which we measured, could provide information on the quark angular momentum, assuming what I showed you earlier is correct. And then looking to the future, the JLab 12GeV neutron experiments in Hall CNA will extend to higher Q squared with more uniform coverage. A dedicated experiment with a transversely polarized target is a worthwhile effort at 12 GeV. Or possibly more measurements with the transversely polarized target in class 12 or solid. And the proposals need to match the expected neutron proposal's precision in order to do any flavor decomposition. And at high X and Q squared, data on G1, G2 is needed to, and I should emphasize, and G2 is needed to cleanly extract the leading twist PDFs. At present, many fits go down to low Q squared, which is not justifiable. So joke is sane 12, insane. Who knows what the experiment will be called. While the future EIC will focus on the C quarks in gluons, JLab will continue to present a unique opportunity for studying QCD and the structure of the nucleon to high precision in the valence region. Thank you for your time.
Can you please go to conclusion 1? Yeah. The flavor independence of the color force would indeed be very surprising because, for example, the Sivers effect we know on up and down chords is approximately equal and opposite in sign. And for the color force enhanced D2, one would expect the same type of pattern.
I suppose instead of flavor, I should have said isospin. The neutron and the proton, the D2 value is indicating that the averaged force is the same, not really the individual flavors.
Okay, in any case, flavor decomposition would provide no insights.
Yes, definitely. I'm not saying that the forces are the same. I'm saying that the average for the proton and the neutron are looking the same. That is, they're going negative. So if it's QCD that's doing that, right, there's no reason to expect them to be different because it's just the core content is different. Nothing to do with QCD at all.
Just to comment on your question about when these higher twists start to show up. I think the more correct question will be when they don't show up, because what we have seen going to compass, PP, elsewhere, all the azimuthal, most of the single spin and azimuthal asymmetries are they can exist only if there is a higher twist, so no correlations. So we have a bunch of observables at a very different.
That's right, and that's why I would say this point here is that you need higher x and higher q squared to say this as well. So if you make the assumption now that at some moderately high q squared that there's no higher twists, you might be fooling yourself. And if you just are doing if you're just doing the longitudinal PDFs and calling that just leading twist. That's what
the point is that so you in this particular observable you have leading plus subleading, but there are a bunch of observables where there is no any leading, so it's just the higher twist.
Mm-hmm.
So where it's obvious that you have.
Okay, I think I understand what you're saying.
Just a quick comment about the previous discussion about the flavor dependence twist D2. We're actually in the process of performing global analysis of the world's data, including the results of Witt's experiment, to try to, for the first time, extract the X dependence of the U and D twist redistribution.
I know that I've said this to you before, but the important ingredient that is lacking in your fit is the twist 3 evolution. And if you don't have the twist 3 evolution, you have no q squared dependence, and you can't answer that question, or the inverse of it, when the higher twists start to matter.
Great. With that, we're going to end this session and go to lunch. We will be reconvening at 2 o'clock. So let's thank all of our speakers one last time.
You've seen the talks and you've seen them get their awards and grab their checks and run, or maybe not, maybe some are here. So we have the Postdoctoral Research Prize for Aldrin Seno. And the one thing I'll mention here is in the past there's been a little confusion of it about this. Many people have interpreted it as a new standalone research program that has to be fully funded within the sort of 10K scope of the award. Of course, that makes it hard to put together a proposal that is outstanding and yet fully accomplished in 10K. It also means that people felt that it had to involve something different from what they were already doing, which meant the postdoc supervisors weren't always as supportive of it as they might have been. I don't think it wasn't really ever intended to be something quite like that, so we've tried to make it a little more clear this year, and we'll do a little more in the future, that it doesn't have to be completely standalone, and it doesn't have to be fully within the 10K budget. You're sort of putting in a proposal for the 10K research support to help with the program you have. Obviously, new and novel and interesting ideas are great. It's something where that 10K makes all the difference, helps the proposal, but it's not really meant to exclude efforts that sort of help the main projects that we might already be working on. And so, you've already seen the presentation on the research, and there'll be a story in an upcoming on target. So, again, my thanks to the Users Group Board who judged the award and JSA for funding this, as well as all of the postdocs who put together research proposals. Again, you've seen both the recipients and plots from the thesis prize winners. In this case, the Users Group Board does the first round of judging and selects 3 finalists. The final panel changes every year, and this year it was Roy Holt, Mayan Gao, and Juana Nicolescu, who went through, and despite their great abilities, they were unable to narrow it down to just one, because we had 2 outstanding winners this time, and so the prize was split. Again, you've seen the presentations, there'll be a write-up on target, and again, thanks to all of the advisors who put forth the students and their theses, the judging committee, and again, JSA for funding this. So on Monday, you saw hot off the presses the winners of the poster prize competition. Again, this is through the Initiative Fund. This year we had 18 entries, very good participation. That was in part thanks to the interest of the students and their advisors, and in also large part due to Melissa and Lorelei going out and making sure that people knew about it and were submitting posters. One of the differences this year is that in addition to the cash award, there's also for all 3 winners a $500 travel support, so they can attend a meeting, perhaps present the poster, perhaps give a talk, or just get out and see more. So we thought this might be both useful as far as getting exposure, getting sort of more exposure for the lab, students who put together very impressive presentations, and also again, it can kind of help the advisors and hopefully encourage them to get their students to participate. Don't know how much effect that had, but we did have a very nice turnout this year. There are also the graduate student fellowships. The list was flashed up in Jerry's talk briefly. This is a JSA Initiative Fund proposal, so we don't have anything to do with this, but we always like to highlight the high-quality graduate students that we have coming in who are, in this case, receiving support through this fellowship program. There's a wide range of physics going on here, and 3 of the recipients this time were recipients last time who are doing their 2nd year. Each year it's evaluated independently. And so again, that's something else that even though we don't put in the proposal, that's an Initiative Fund supported project. So as I mentioned, last year, there were sort of 2 major changes to the bylaws that were presented to the users group. One was this change of the chair line to go from a 2-person chair line to 4. Basically, it means that you only have a person serving as chair serves only 1 year. Maybe doesn't pick up as much experience, but you end up having 2 years serving on the board before taking over as chair. There are other members who are paying attention, and we thought in particular sort of for helping the continuity of having more members that were on for more than just 2 years. So that was strongly supported in the vote last year. We also brought in the non-discrimination statement. and that also passed no problem. As I think about it, I'm not actually sure if you would see any of these changes if you went to look at the bylaws, because at some point someone has to actually change them, and that probably should have been me. But so anyone who wants the no prize can go ahead and look and tell me if these have changed or not, and complain, because that's what we're here for, among other things, hearing your complaints and hopefully doing something about them. And so both of these were presented last year and then passed in election by email. One of the major efforts that the user group board is involved in, and in particular over the last several years, is various forms of outreach. There have been, in the past few years, we participated in this Nuclear Physics Day on Capitol Hill. These visits, these are combined visits from users at Michigan State or FRIB and RIC and JLab. We participated just in the last 3 years. They've been going on longer. As you can see, our participation has been growing significantly each year, and we're getting a little better at coordinating the timing and finding users in advance. Dipankar is the outgoing board member who is in charge of outreach, so he's had a significant role in this. He's made available a lot of the information from these programs, and we'll try and continue to put more information available so people who want to know more about this or want just general information for any kind of efforts of their own will have that available. He also put in an initiative fund proposal last year to help to provide travel support for people who want to participate here. These trips can't always be paid from the grants, so we also want to encourage, we want to have some money available. We also want to encourage people to maybe talk to their universities if they want to participate, to see if the universities are interested in contributing some to that. So Nadia will be the board member taking this, the outreach role over this year. And we also hope to put together sort of a permanent committee on outreach as our efforts are getting somewhat more extensive. We want to have a little more continuity so that we want to keep people who've been involved in the past, as well as bring in new people who are interested in participating. Prior to Dipankar, Ken Paschke was working in this, and he was also very helpful in sort of getting Dipankar and I up to speed on the efforts that have gone on before, and hopefully he'll continue involvement as well. So in addition to these managing these direct trips, we also try and make sure, at least when important issues come up, we want to try and contact the users and make sure users are aware of such things, and just sort of try and make it easier for people who want to do outreach, whether it's trips to Congress or just broader outreach. There's also, for the past few years, NUFO, National User Facility Organization, has organized this science exhibition on Capitol Hill. That's taking place in June, and we've been sending 1 or 2 people along to participate in that. NUFO is going through a reorganization, so exactly what happens this year and what it will look like in the future is still up to date. We'll be sort of keeping an eye on other events like that we don't have any direct involvement in putting together, but where we think we can get involved and be helpful. So one thing I talked about last year was sort of general ways to try and improve the visibility of the program. We were hoping to find people who thought that they could give, that they had good talks that sort of covered more than just the latest experiment, and were sort of covering a big part of the program for a broader audience. So we got a few people who said they'd be interested. We haven't done too much with that. One thing we want to do is sort of collect people who can give a good presentation like that to an outside audience, but also see about trying to find ways to look for speaking opportunities or recommend speakers or topics for seminars or colloquia at various universities, especially areas where there isn't a strong JLab contingent already. So we are still looking for people who are interested in doing this, people who are maybe interested in helping to organize things like this in the future, so we can bring together people who are willing to talk and maybe sort of connect them with institutes that are looking for nice overviews of various areas of the program, in particular those highlighting the activity they have going on. It's also very important for both NSF and DOE to have these highlights. For NSF, they have these nuggets. Those are submitted by the NSF-funded institution. With DOE, a lot of them are highlights that go through the lab. But if you have good results that are coming out, if you have something that you think makes a very nice story to an outside community, it's really worth working with the NSF or with the lab to put together one of these nuggets, these highlights. And again, you can, the lab will be happy to assist in putting these together, whether they're submitting it or you are, but I think it's very nice to sort of have these, and we might also want to see about collecting these and making them available, or versions that might be better for a physics community than a funding agency. So I said we talked about creating permanent subcommittees, perhaps one on communication, one on outreach, again, to try and help improve the continuity when we meet again tonight in the unair-conditioned small room with the door that doesn't open very far. We'll discuss. So we have two new chair line members, so I think the idea is to sort of spread out some of the activities that the chair is responsible for and try and help them coordinate these committees so we get more people involved and it's easier to start new programs. So for all of this, ideas are, things are still under discussion. We're very happy to have input and ideas from people, and if you're interested in getting involved, you don't have to be on the board to get involved in some of these aspects. In the past, we've had previous board members, as I say, who've continued to help with the outreach efforts, but that's because we knew they were knowledgeable and interested, but we're also looking for other people who might want to participate in this sort of thing in the future. One thing that came up is that we think it's worthwhile at this point to try and collect some user input on video conferencing capabilities at the lab, how well it works if you're here, if you're remote, how the setups in different areas work. So if you have comments on that, you can just go ahead and send those out. What we'd like to do is put together some kind of a survey so we can sort of craft the questions to get maximum input, but that's just an issue that we're looking into at the moment. Last year, we sort of formally tried to start doing a JLab alumni group. We have a lot of students and postdocs who've come through here, and some are interested in continuing on at universities and national labs, and others go into other areas. We have a large base of people who come through and have experience in all sorts of different areas. So to begin with, Ellie was collecting information, also put together Facebook and LinkedIn groups. So at this point, we have 52 independent people who've joined one or another of these. That's starting to be at the point where we can actually maybe do a push to them to try and find more people. But again, certainly anyone who's here now would be an appropriate member of this. If you have students or postdocs who've come through and you think might be interested in being available for discussions, mentoring, networking with other students and postdocs at the lab, please let them know about these. We'll see if we can get up to the point where it's sort of self-sustaining and maybe we can get enough discussion going on within those groups to come up with sort of next generation ideas. So 2 years ago, Mont requested that the users group chair join the Director of Safety Council. At the time, so it was suggested, when I first came out for that, it was suggested that maybe having a local person would be a useful way to go. We're sorting out some of the details, but in fact, Ed Rash, so for the last year and a bit, has been the user representative on this committee. He's been extremely effective. He's now, let's say, at the point where he's getting just sort of unsolicited requests for feedback and advice on various safety issues, and I think it's great that the people working on these issues know him well enough to be able to just go and get informal feedback before rules and procedures get too far advanced. This is essentially what he gave us last year to report on. Just the council is very strongly focused on safety and is really looking carefully at the data. And it's not just brainstorming for new things. It's really looking at what's happening at the lab, looking at what's happening elsewhere, and trying to modify the procedures. And there has been definitely improvement, sort of going towards more openness to help understand these. Yesterday, at last night's board meeting, he gave a very short summary on one new thing. There's a new student supervision policy. I'll go over just this very briefly, but it will apply to all graduate students, undergraduates, and high school students at the lab. And it was established by the Director of Safety Council based on an external safety review. And in fact, I was a member of that safety review as well. So here's the link to the policy manual. This has been implemented, but it's new this year, and it'll have a lot of impact over the summer with students coming in, and they'll sort of use what happens in this time to try and tune up the program and see if there are things that need to be changed. So I won't go through all of this, but I'll just mention, so in the past, there's been a JLab sponsor for all outside users. They are the ones who can approve your computer accounts. It's mostly been an administrative role, but technically they were in principle in charge of many aspects about safety training and things like that. What they've done is sort of moved now to having a JLab sponsor, so you'll have a sponsor who stays the same, but also a supervisor who's more responsible for day-to-day supervision, making sure you know what work you'll be doing, making sure that all the training is there and that the procedures are being followed. So the sponsor will assign a supervisor. If a student finishes one task and starts working in another hole, they'll assign a different supervisor. So the idea is that the supervisor will really be much more aware of what the student is working on and in a good position to be involved with that necessary training. Doesn't mean they have to be working side by side with the student all of the time. So the supervisors will have to be JLab employees, have to have some reasonable knowledge of what work is being done. So depending on the type of work, it could be technical staff, scientific staff, and it could be the sponsor maybe. The sponsor themselves may also be the supervisor. And if a student is not working on hardware projects and not working in an area with hardware things going on, they won't necessarily need a supervisor. So this is all new and it's just been implemented. So there are changes to the registration and training system as well as some guidance on how to work with this. All of the sponsors and supervisors at JLab, so essentially all of the physics division staff will receive this training so that if a student needs to work with someone, they don't have to go back and make sure everyone is trained. And so there will be a system where where safety people will be around the lab, and they might, if they see a student working on some project, might sort of interview them to at least make sure that they know who their supervisor is, have a broad understanding of the work they're doing and the various documents that relate to that. And again, this is new, it's just being implemented now, and so we'll sort of have to see how that goes and see if it's working beautifully or if there are issues that we might want to address to make it easier or more effective in the future. And I think this is something, there are various whole collaboration meetings coming up. It may be that this is something where you want to have a little more detail, so you might want Rolf or Ed or someone from the users group board to come and just give a little bit more detail in this. So I have all the detail that gave me in the slides. Didn't want to go through it all here, but at least let people know this was coming up. And I'm sure as students are coming in for the summer, we'll get a much better feel of how this works. Okay, so some external announcements. So the INT, Institute for Nuclear Theory, has their proposal deadline coming up in July. So if you are interested in that, certainly feel free to submit. I'm currently on the advisory committee, and if you're planning on submitting something and you haven't let one of the advisory committee members know, it's useful to let us know just so we know what's coming in. We can also potentially give you, answer questions you have about the procedure, what we're looking for. And this is evaluating 1 week or short programs that will occur next year and longer programs that will occur 2 years out. 95% sure that that's correct, but definitely make sure you check that there. In addition, next year I and Susan Gardner will be rotating off the committee, so we're always looking for lists of good candidates. And so if you have ideas for people who would be on the committee, do a good job representing hadronic physics and other aspects we do here, it's certainly good to have people who understand the program on the committee. Topical Group on Hadronic Physics is having a membership drive. So we have a sign-up sheet here. If you put your name and email address, you will magically become a member of the Topical Group on Hadronic Physics. Or you can just email me and let me know. So the Topical Group on Hadronic Physics is one of the many topical groups. I'm involved with this one, which is why the announcement is here. But of course, there's the few-body topical group. There's fundamental or precision measurements. So I think they have a strong role, and it's nice to have involvement in these groups. In particular, with the Topical Group on Hadronic Physics, They have a thesis prize. They get to submit two members for APS fellowship each year. And over the last several years, there are quite a few people at JLab who've received fellowships, or in the JLab user community, who received fellowships nominated through the top of the group on hadronic physics. Also try and send out updates, information that's relevant to the hadronic physics community. So for example, just this week, we sent out an update on the situation with Panda. I'm not sure how familiar people are with that, but there was a review of the project there, trying to ensure that the project would be completed within the now fixed budget. And Panda came out at the bottom of that for a variety of reasons. And so there is a serious possibility that the project will be canceled. And that's something that we were asked to sort of make sure that people were aware of, and if they had feelings on that, they could pass that along. So we try and do that. I think that's probably something that also the users group might want to send around, because a lot of people who aren't members of the GHP might still be interested in details on that. I mentioned this in the past, but this week I found that still many people aren't aware of it. So there's this Hadronic Physics conference page. It used to be this Baryon Resonance Analysis Group conference page, but we took it over, and so really anything that's of interest to a significant part of the JLab community should be on there. We try very hard to put up meetings as soon as we have information. It's good if you want to schedule a meeting that's not occurring at the same time as another meeting, and hopefully it's one-stop shopping for workshops, collaboration meetings, and so forth. Of interest to the community, and you can send information to me or Mark Manley about conferences that are coming up or additional information. Finally, as I said, I think it's definitely important to consider both membership and service in the various APS units that are relevant to your physics. In the DNP, we have some suggested members for the nominating committee. Nomination forms are here or at the front desk. Also, the executive committee assigns or picks people for various other committees, so if you have ideas or are interested in serving on other committees, you can send those ideas on. And we don't actively do this for the topical groups, but again, if you have ideas for members or you're interested in serving, you should definitely let the relevant committees know about that. So the very sort of main summary, there's been a lot going on in the last year. A lot of the talks here focused, of course, on all of the progress with 12 JEV upgrade. There's been a lot, but of course that's been happening in a very busy background. The long-range plan, the resolution meeting, and so the final language is being put together, and we'll hear about that. But even so, even with that process starting to wrap up, it's going to be vital to continue to make the case for the 12 JEV program, share our exciting science. We're going to have to spend a lot of time making sure we can get that science out as quickly as we can, but we still need to be active about letting people know about it, while at the same time taking our vision for an electron-ion collider, sharpening up the physics case, and making sure that we make a strong case for that as well. So it will be very busy times, but very exciting times, and as we move in, we get the accelerator and the holes and equipment going. We're in an excellent position to go ahead and start making some groundbreaking physics and transformational discoveries. So that's it. Just some final reminders. This is the list of sort of user board suggested nominees for the DNP Executive Committee. I would like to thank Dipankar Dutta, who's done an excellent job of organizing this meeting, and Melissa Cummings, who organized the poster session and a lot of the student activities. I end up being up here in front of you, but Dipankar really did an amazing job of putting everything together and organizing everything. And finally, I really want to go out of my way to acknowledge Lorelei Chopard. She's been, of course, also critical in organizing this meeting, but really, over the past 3 years, she's just made exceptional contributions to the Users Group Board at all of our organization's activities and discussion, and has also been just outstanding in dealing with user issues. And we know that users have lots of issues. So, thanks again, Lorelei. All right, I am no longer your user board chair, so questions for myself or the
I would like to, on behalf of all of us, to thank John for his outstanding leadership in the last, how long? 3 years, and I'm so happy that I will only be chair for 1 year. Again, thanks to John.
All right, questions, comments? All right, let's look back to physics.
Great, with that, that ends this session, but we immediately go into our next session. So our next chair is Lisa.
Okay, so welcome to the last session of the meeting. Our first talk will be by Matthias Berger. He'll be talking about orbital angular momentum.
Very much for the invitation to speak here. The nucleon spin puzzle. Since the 80s, we know that only 30% of the nucleon spin is due to the quark spins, and that the nucleon looks slightly more complicated. On Monday, you heard already Marco talk about the gluon spin contribution. And you will probably remember this graph, and I don't want to elaborate on that anymore. Instead, I want to focus on the quark orbital angular momentum. Questions like how can one measure it? Obviously, one needs to probe some correlation between position and momentum. And then there are also some issues about exactly how the quark orbital angular momentum is defined. The key experiment that we hope will shed some light on quark orbital is deeply virtual quantum scattering. And if we look at form factor experiments, then one of the physics information we get out of form factor experiments is by Fourier transform with respect to the momentum transfer, we can get information about the position of the quarks. Deeply virtual quantum scattering provides a more surgical approach. Since there's this additional quark propagator there, they are also sensitive to the momentum of the quark. And that, at the same time, there's a momentum transfer involved. So by doing appropriate Fourier transforms, we also get position space information. And that's why the deeply virtual quantum scattering and the generalized pattern distributions that are probed in these processes are allowed to get some simultaneous information about position and momentum of the active quarks, which is what we need for orbital angular momentum. The physics of generalized pattern distributions was already mentioned by Anatoly Radyushkin. In the limit c going to 0, the 2E Fourier transform of generalized pattern distributions provides information about distributions in impact parameter space, and at the same time, dependence on the quark momentum fraction. In the case of unpolarized nucleons, it's the Fourier transform of H, which is the momentum dissected Dirac form factor F1 that provides the position space information. In the case of transversely polarized nucleons, here for nucleons polarized in the x direction, one should no longer expect an axial symmetry of the impact parameter dependent quark distributions, simply because the nucleon spin singles out a transverse space direction. The details of the transverse deformation are described by the transverse gradient of the Fourier transform of the GPD E, where E is what you get when you momentum dissect the Pauli form factor F2. The physical origin of this deformation is illustrated up here. if you have quark currents that are correlated with the nucleon spin, then a virtual photon sees an enhancement of the quark distribution on the sides where the currents are coming towards the virtual photon, and the suppression where it goes away. And the reason is simply that the relevant quark densities in DIS, in the Birkin limit, are the gamma plus component, which is the 0 plus Z component. The average shifts that you expect from this effect are quite large, and indeed, one can model independently relate the transverse flavor dipole moment for each quark flavor to the contribution from that quark flavor to the nuclear anomalous magnetic moment. And those can be, if one neglects the strange quark contribution, which is probably fine at the 10% level, then one can use the measured proton and neutron anomalous magnetic moments to get the transverse flavor dipole moments. Now, we're interested in quark angular momentum. If I look at the x component of the angular momentum, that's y times the momentum in the z direction minus z times the momentum in the y direction. These generalized parton distributions embody a simultaneous distribution of the momentum in the z direction and the position in the transverse direction. So using generalized parton distributions, it should be easy to evaluate the first term here. The second term would be more tricky. However, if one makes use of the fact that in a rotationally invariant state, a state that's invariant under rotations about the x-axis, up to a sign, the expectation values of the two terms are equal. And instead of evaluating both of them and taking the difference, you can just evaluate the first one and multiply by 2. And if at the same time you use the transverse deformations of the parton distributions in impact space, that allows you to quote-unquote rederive the G relation, which is written down here. Now, having said that, there's an issue one needs to address in the context of angular momentum, and that's how exactly it is defined. And this looks very complicated, but if you don't try to understand the details, it should be no problem. Let's start out with an expression for the angular momentum carried by the photons in QED. R cross the momentum density integrated over all space. In the first step, I'm rewriting the magnetic field as a curl of a vector potential. In the second step, I'm simplifying the first two crosses of the double cross product using just back minus cap. And then in the next step, I'm leaving the first term unchanged, and in the second term, I'm doing an integration by parts. So I get two terms, one where the divergence acts on the electric field, and one where the divergence eats the position vector. That's this term right here. Now finally, I use the equations of motion, that the divergence of the electric field is equal to the charge density, replacing this term by the one down here. And what I've done looks like magic. I've started from something that involves only photons, and I ended up with something that involves one term that contains both the electron field and the photons, one term, R cross a gradient, that has the physical interpretation as the photon orbital angular momentum, and a second term that contains no explicit position vector. It acts only on internal degrees of freedom. That one has the interpretation of the photon spin. And so by transforming this one into a term containing the photon orbital and the photon spin, I've generated a term which cancels a similar term in the local manifestly gauge invariant definition of the quark orbital angular momentum. And that simple example illustrates the difference between the G decomposition for the nucleon spin and the Jaffe-Manoa decomposition of the nucleon spin. And in G decomposition, you have R cross the pointing momentum in the definition of the gluon total angular momentum. In the Jaffe-Manoa decomposition, the integration by parts and equations of motion are used as illustrated on the previous slide to generate a gluon spin term and a gluon orbital term, but at the same time the vector potential here has disappeared. These are the expressions in light cone gauge. One can write manifestly gauge invariant expressions down, which I won't do, which are slightly more complicated. Now, why should that worry us? Well, one reason is the experiments to be performed here that should allow us to access the quark orbital angular momentum entering the G decomposition. At the same time, there are experiments done at Brookhaven that allow to access the gluon spin, and by subtraction from the gluon and the quark spin from 1/2, one could thus access the sum of quark plus gluon orbital angular momentum. Ideally, we would like to mix these results to obtain a complete decomposition of the nucleon spin. However, already a simple calculation in QED for an electron illustrates that the two definition of the quark orbital angular momentum here and here give different numbers. And those numbers of the same order in alpha as the electron orbital in the various definitions. So there's no a priori reason to neglect the difference when looking at these orbital angular momentum. And given that we know there is a difference between these two definitions, the question is, what does it represent? Or how can we study it? A breakthrough in this direction came using Wigner distributions to define orbital angular momentum. The reason this allowed a breakthrough is because it allowed to study the orbital angular momentum defined in both definitions using the same framework, and then one could easily look at the difference. And these Wigner distributions, they are defined as non-forward matrix elements of some correlation function. We need to look at a non-forward matrix element here because we want position information. So just like in the case of a form factor, by having a momentum transfer involved in doing a Fourier transform, you get position information. The non-locality is necessary because momentum distribution expressed in position space requires a non-local correlation function. And as usual with Wigner distributions, by integrating over position or momentum, one gets just the momentum distributions or the position distributions respectively. If you have the Wigner distributions, it's easy to calculate the orbital angular momentum by simply taking the cross product between position and momentum and integrating of all variables. The gauge invariance requires, once we have a non-local correlation function, to throw in a Wilson line gauge link to connect those 2 points. And the resulting Wigner distributions will in general depend on your choice of path of doing that. Well, there are infinitely many choices. One is an perhaps natural choice would be a straight line, shortest distance between these 2 points. And it turns out if you do that, you get the G definition of the quark orbital angular momentum with this local manifestly gauge invariant derivative. However, in many applications, it's also natural to use a light cone staple where you go from the position of one quark field operator along the light cone to infinity, and then back at the transverse position of the other quark field operator. And the reason this is sometimes the preferred choice is that, for example, in single spinor symmetries, when you probe quark transverse momentum, what you measure includes the final state interactions acting on the escaping quarks. And those final state interactions are embodied in these links to light cone infinity. So if one wants to have transverse momentum dependent quark distributions that include the final state interactions and hence can be compared to your experimental results, you have no choice, you must use these light cone staples. Now we're in a position to compare the 2 definitions of orbital angular momentum directly. And I've shown you this one several times. Here I have now written the Jaffe-Manoa definition in a manifestly gauge invariant form. The first term is identical to what appears in the G decomposition. And then there's this integral of the plus perp component of the field strength, color field strength tensor along the light cone. This one arises from that light cone staple to infinity. And when you take the difference, what remains is just this second term here crossed with the position vector. And so now we can answer the question, what is the difference between the Jaffe-Manoa versus G definition of the orbital angular momentum? It's the matrix element of the quark density correlated with this cross product. And to understand what the cross product means, I'm writing this out in terms of the usual spatial components of electric and magnetic fields. And what one finds is the same linear combination of electric and magnetic fields that you get for a particle that moves with the velocity of light in the minus z direction. Which means that what's in this, what's crossed with the position vector is the transverse Lorentz force on the ejected quark integrated along its trajectory to light cone infinity. And because of the cross product, that's the torque. And for relativistic particle, distance is time, and when we integrate over the torque, we get the change in the orbital angular momentum. So the physics of this difference here is the change in the orbital angular momentum of the escaping quark. If you want, you can think of the G orbital angular momentum as the local orbital angular momentum inside the hadron, whereas the Jaffe-Manoa orbital angular momentum is the one that you would hypothetically measure at z equals minus infinity. And that you should expect that difference to be non-zero can be illustrated by just looking at the simple dipole field. So let's imagine there's a magnetic colored dipole field inside the nucleon that's correlated with the nucleon spin, and we're ejecting an ensemble of quarks, which I've indicated here. And if you're doing your right-hand rule, what you can convince yourself is that the Lorentz force on this quark is into the screen, and the Lorentz force on that quark would be out of the screen. And if you imagine now starting from an ensemble of quarks, then on the right what's shown is the top view of what's happening on the left. you can easily see that there's a net torque on this ensemble of quarks. That's very nice, but where does this insight help us? Well, first it lets us understand the QED calculation that I mentioned earlier. In the QED calculation, the orbital angular momentum in the Jaffe-Manohar decomposition came out a little bit larger than the one in the G decomposition, the difference being alpha over 3 pi. And the fact that this is a positive number, you can convince yourself by simply drawing the magnetic dipole field around an electron due to its magnetic moment, and then doing the right-hand rule, watching the signs, etc. QCD, what should we expect there on a qualitative level? Well, in QCD, since the composite system, there would be several effects. One is the self-effect that we observed already for an electron, that there's a change in the orbital angular momentum due to the electron or quark escaping through their own dipole field. And that should have the same sign, except it's of course correlated with the quark spin rather than the target spin. And therefore there should be a negative effect for down quarks. With the spectators, they of course also create magnetic fields which should have an effect, and take into consideration an extra minus sign due to the attractive color forces. One should expect a negative effect both for up and down quarks, a larger effect for down quarks, simply because they see more magnetic field from the up quarks that have their magnetic field all in the same direction. They're asking, well, could one get some local information about this torque? This is going to be difficult because the most simple local operator that gives information about this torque would be the third moment of a twist 3 distribution. There's a similar object familiar from transverse single spin asymmetries. Some long time ago, Chu and Sturman have studied a matrix element that looks very similar to what I've shown you here. The only difference is it doesn't involve this cross product with the position. So semi-classically, this so-called Chu-Sturman matrix element or Chu-Sturman integral, what it represents is the transverse force acting on the escaping quark in DIS experiment. And it's no surprise that this transverse force integrated along the trajectory, which gives you the impulse due to the final state interaction, plays a crucial role in transverse single spin asymmetries because you don't have any net transverse momentum to start with. If you look only at the first integration point of the Chu-Sturman integral, you're looking at the force at the beginning of the trajectory, which was mentioned this morning by Whitney Armstrong, because that matrix element happens to appear in the x-squared moment of the twist 3 part of the polarized parton distribution G2. And that's why the measurement of G2 will give us some insight on the transverse forces acting on an escaping quark. Already before doing the measurement, we can gain some insights from this from this equation here that relates the transverse force to the D2 matrix element. First of all, from this picture here of the deformed distributions, one can anticipate the sign of the force. Namely, if you assume that the force on the escaping quarks from the spectators is attractive, then in this case, if you would strike an up quark, then the up quark would on average experience a net force that's down, and for the down quarks, it's in the opposite direction. That alone allows to make prediction about the signs of D2, which should be opposite for up and down quarks. This relation should also tell us something about the expected size or magnitude of D2, because this factor 2m squared is a big number. I've written here in units of 10 GeV per Fermi because that's a unit that I can visualize. The string tension, which is when all spectators pull in one direction, is about 1 GeV per Fermi. So the unit here is 10 times the string tension. But in a single spinor symmetry, we wouldn't expect a large net force because there's some cancellation. So we would expect a force that's an order of magnitude smaller than the string tension. And therefore, and that's the reason why the D2 measurements and calculations turn out numbers that are on the order of 0.01. And this was not a prediction, it's a post-diction, but it's consistent with what we know from experiments, model calculations, and lattice QCD calculations. And it perhaps sheds some light on the observation that the Vansura-Wilczek approximation works so well. And finally, here's my summary. I've discussed the connection between GPDs that are probed in deeper virtual quantum scattering and the distributions of quarks in impact parameter space. Those get deformed when you have transverse polarization phenomenon. And GPDs, one of the physics aspects that they embody is simultaneous information about transverse position and longitudinal momentum of the quarks, which provides an intuitive derivation of the G relation. The difference between the Jaffe-Manoa and the G orbital angular momentum can be interpreted as the change in the orbital angular momentum of the quark as it escapes from the nucleon. And finally, I discussed the connection between D2, the expert moment of the 2s3 part of G2, and the transverse force on quarks in the AS experiments. May the talk be with you.
Do we have any questions?
Right, so if the difference in these two definitions of orbital angular momentum have to do with the quark leaving the nucleon, does that mean that at least one of the definitions cannot be understood with external interaction?
I'm not sure I understand.
You notice, can a quark start leaving the nucleus without an external interaction?
No, there will always be some finding state interactions, and the orbital angular momentum in the Jaffe-Manoa decomposition has that included.
Can you comment on the size of the transverse force versus the size of the transverse impulse, in that which is bigger, or which is the dominant? Is the force, the transverse force D2, larger than or as on the same order of magnitude as the impulse, or does as it leaves, does the force grow, or does it shrink?
Well, the force at some point stops. That's when the string breaks. The question is, how long does the force last? How long is it significantly different from zero? And if you use ballpark figures for the force obtained from what we know about D2, and you use ballpark figures from what we know about transverse spinor symmetries that give you typical average transverse momenta of 100 MeV, that gives you information about the range of about 1 to 2 Fermi. So think about a force between 50 and 100 MeV per Fermi, and a range of 1 to 2 Fermi, and an impulse of about 100 MeV.
I guess my question was also, does the force grow before it shrinks?
I don't know. My gut feeling is it wouldn't, but honestly, I don't know.
Matthias, what kind of changes do you expect on your forces when you go to hierarchy square, lower x? Higher energies of quarks.
Yeah. What I expect intuitively is that the long-range forces will get washed out, they will disappear. The reason is that at higher Q squared you get more color floating around, you lose the long-range color coherence of the nucleon wave function. So that picture of the spectators on the other side pulling in that direction, that is going to disappear at large Q squared, simply because you lose color coherence. And so bottom line being, one would expect those effects to die away quickly.
Since coming back to this, the quark leaving the nucleon, giving this change. So if I use DBCS where the quark doesn't leave the nucleon, I measure only then one part, or which part do I measure when I insist on DBCS?
The intrinsic one.
The intrinsic part, yes. Yeah. So, okay, so that's a significant difference, right? So, yes. Because we have heard on Monday there is no orbital angular momentum, and now I hear, which I like, that depends on what you measure, right? And so, the statement that angular momentum overall is 0 for quarks.
Well, as Tony Thomas already criticized, I think you have to take that result with several grains of salt. I mean, that the conclusion that the quark orbital is 0 according to this global fit that Marco showed. It's the error bands are so wide that and going to Q squared to 10 is an ad hoc choice. Why not 4? Why not 20?
I certainly agree with that, but you know, this is the kind of thing that makes it into New York Times and CNN or whatever you show, right? And the error bar doesn't make it there; it only makes the statement, right? We have solved the problem. And but the other question I have is from your there's a difference between D and U quarks in this whole evaluation. Would you expect a significant difference, in particular a sign difference between U and D?
Well, this is what I try to do here. I think one has to do model calculations because the self-effect I expect to be negative for U quarks and positive for U quarks, negative for D quarks. The interaction with the spectators negative in both cases, but larger for D quarks. If you add that up, you get a big negative effect for D quarks and a partial cancellation for the U quarks, where without doing a model calculation, I wouldn't dare to predict the sign. So I would expect a difference between U and D quarks, and if you add up the effects for U plus D quarks, I would expect a net negative effect. So the Jaffe-Manova net quark orbital angular momentum should be more negative or smaller than the G net quark orbital. I think that's a safe statement that one can do without a detailed calculation.
Thank our speaker. Our next talk will be JP Chen talking about, or giving us an overview of the solid experiment.
Okay, I'd like to thank the organizer to give me a chance to talk about the project, the experiment, a group of experiment program with solid, which many of us have been working on this for several years. Probably a lot of people have heard of this, but I just want to give you a little more detail what are the programs and why we need this and what's the kind of status. So we have, I will start with some introductions, mainly why we want to have this. Then I will go through the approved programs. The big part of this is the solid program. We have 3 approved experiments plus 2 approved run group experiments. And then there's one PVDS approved experiment and another GSI threshold production experiment. And just recently, they are on the development. There are a few other experiments, GPDs, and also we had consider some EMC effect with the pattern variations. I'll give you some kind of status about where we stand. Okay, first, why solid? This slide Mount showed yesterday. We have a very nice 12 GeV upgrade. Is right almost finished. So the 4 hours we all have some upgrade. RB has gone from class 6 to class 12, and RB we focus on ROX and maybe some other physics as well. RC has a new HMS with a new super HMS together with the HMS, and a very nice study on the valence part. For A, we have some minor upgrade of beamline, and then we're looking into more delicate upgrade like so big byte and also solid and modular. But why solid? Where when we do 6 GeV experiment, we all know JLab has the very unique features with the precision measurement. The took experiment often take 1 day of data. It's worth all the existing world data for some of the measurement. So it's thanks for the really nice beam and detectors. We have very high luminosity. We also have large acceptance detectors. But in the 6 GeV, these 2 are often not totally combined. You can see when we involve A and C, we have very high luminosity, go all the way to 1039. But acceptance is always small. The spectrometer has typically less than 10 radians solid angles. So we try to now do with big byte, super big byte, but still only increase by some limited amount. While in Hall B, class 6 has a very large acceptance, but luminosity is limited. So with the JLab 12 GB upgrade, really will open up very nice opportunities. In particular, we can do GIS, which 6 GB, we only have the corner. Now we can very wide range. We can do all the nice GIS, inclusive GIS, deep exclusive process. Give us, we probably should provide the best and most precise information on the valence part of the structure of the nucleon and many other high-impact physics. But when we go up, we try to do multi-dimensional study, you really need much more statistics, precisions. We know how important it is. That really would like to have not only high luminosity, but large acceptance goes with high luminosity. That's what class 12 planned to do, and did. They increased by order of magnitude in luminosity upgrade by focusing more in the forward angle, which with energy upgrade, physics is more going forward. And to fully take advantage of JLab 12 GB, we would like to do better even. And with the new development of all the technologies like detectors, DAQs, so we like to have a detector which can handle even more than class 12 can handle. And that's where the solid is, which will be able to handle 10 to 37 without any buffers. If we add some shielding buffers, we can do parity validation with 10 to 39. Okay, so that's the reason we started the program of semi-inclusive GIS to multi-dimension precision measurement and parity validation, very high luminosity required, and still with a large range of kinematics we need. That leads to the concept of this solid. We have 5 highly rated experiments get approved in the last few years, and there are more coming, and including some room group powders. And the collaboration really grew to be more than 250 collaborators now from many institutions, many different countries. So I tell you about the program. Start with the TMDs, and this is trying to study 3D structures. And you already heard from Matthias' talk and also some other talks. Now we try to understand the nuclear structure from the big distribution, which is 5-dimensional. Right? This gives you a very complete description of your nucleons. But of course, we can, so far, at least we don't have any direct way to measure this. But if we integrate out some of the kinematics, then you come down to the known part which we can actually measure. One is TMDs. One is the GPD in the impact parameter space. If you do Fourier transform, you get back to the normal GPDs. And they actually come to be something which we are familiar with, the regular PDFs and the form factors related to all of these if you integrate some of them further out. So the part of leading all the, many of you probably see this a lot. For TMDs, if you integrate out the transverse momentum dependence with the deep elastic scaling, you have very large momentum in one dimension, and then you get the known unpolarized, non-chain polarized distributions, as well as one more, which is transverse polarized distribution, pocket transverse polarized, inside polarized transverse polarized nucleon. The distribution will be similar to G1, except when you're relativistic, they're not the same. So this gives you a learn about the future of relativities. But they have a lot more of that. All these additional terms, when you don't integrate transverse momentum, they're non-zero. they really provide very rich information about the spin and the orbit, how they coupled, how they correlated. So every single piece gives you more information, very rich information about their European structures. If we do transverse polarized target, we can get 4 of them. It's probably one of the richest way to do it. But in principle, doing semi-inclusive GIS, we can get all of them. Continuous polarized and unpolarized, we get all the information. The study of TMDs has become quite popular, and it's getting very hot in the last several years, maybe a decade. Access TMDs, you can, it's a worldwide effort. You can do it with a semi-inclusive GIS, which probably one of the best ways. The other one is also very convenient to use QRYAN, but not experimentally, it's very difficult. So far, the first QRYAN is not explored proton, but high-end proton just being carried out at the campus, while there's others being proposed but not being done yet. To the semi-inclusive GIS, you get TMDs, but it's convoluted with fragmentation functions. So the fragmentation function you can get from E plus E minus. So this combined together give you complete information you can access to all the TMDs. There are also very interesting QCD features of that. This generates a lot of theoretical interest. We have a workshop here last week. We focused on the evolution of this part about TMDs. And there's some interesting predictions we can test, which tells us about QCD dynamics. So the semi-inclusive GIS is really a very nice tool. By tagging the outgoing hadrons and also look at their angular distributions that can tell you about the initial how the parton transverse momentum distributions. So by use, for example, we use unpolarized beam on transverse polarized target, you will have in the leading twist, we have 3 terms, and these 3 terms, by looking at angular modulation, you detect your hadron and your spin, and you can actually set them out very cleanly. And each one will give you these 3 different TMDs. Collins give you the transversity, convoluted with the Collins distribution function. The Sivers is the Sivers distribution convoluted with the regular fragmentation functions. And periodicity give you the other ones, the periodicity distributions. So all of this, it's very clean. You can actually experimentally separate them out very nicely. So this has been done in the last maybe a few years, less than 10 years. Already started this exploratory experiment at Hermes and Compass. These are the Collins asymmetries. And theorists already worked, combine all the world data, made some fit with, of course, still with some assumptions. They can give you some initial idea how the transversely look like. So we did the 6GeV experiment, the first also exploratory experiment. So it's not very precise, but already can tell us the sign for, this is on polar team 3, the first neutron results. And it's the Collins and the Sivers, and on pi plus and pi minus, you can see some feature agree with the global fit predictions. We get both of these, and one experiment, even though it's not very precise, we already learned a lot how to do this kind of experiment, and we also extract many different results. We already published 6 PIL, PRC articles, and the 7th one is being considered. So this is very productive. And we also trained a lot of good students. So for 12GeV, you want to go to the real precisions. We mentioned we really need high luminosity and light acceptance. You can see with solid how well we can do. And we have 3 approved experiments, 2 with polarized helium-3, transversely polarized and non-chain polarized, and one with a transversely polarized proton. There is already one non-chain polarized proton approved with class 12. So this combined together we have very complete information. So just to give you some sense how much data, how precise we can get. This is one being of Q square, one being of Z out of many beings. But you also plot versus for different PT and X. You can see these are the projected precision of statistical precision of our data compared with 6 GeV data. That each points odds make it better. And then we have over 1,400 data points where we can get with 90 days of learning, we can get this amount. And combine this with our proton data, with other world data, we can extract Collins fragmentation where we get the transversity, and from transversity to the integration you can get this so-called tensor charge. This is one of the fundamental property of your nuclear, which theorists can take it, like lattice QCD already have predictions. And experiment where some assumptions people already try to extract this, but uncertainties depends on the assumption can be as large as the whole panel, as well as if some other assumption they can be smaller. But we want to do as much modeling as possible with our percent data. This is projected much smaller error bars. And there are many other model predictions, Dyson Schwinger and some other models. You can also see we can get seamless functions. This now we project onto one dimension. From the current projected uncertainties, people extract with model, and to what we're going to do, we can get much better. And in addition to that, I also want to mention how we can learn about the orbital motion and the orbital angular momentum. And by doing these class terms called one gear, and also the other term called the velocity, you can learn about the orbital angular momentum changed by 1 unit or 2 units. So their asymmetry are really determined by delta I equal 2 or delta I equal 1. So you know SP wave inference or SD wave inference. So by doing that, your data combine all of this really help you to pin down what's the S wave, P wave, or possible D wave contribution of your proton wave functions. Of course, within this proton model, you can learn very well how different the orbital components are. So this is this is actually very difficult measurement for velocity. It's very tiny asymmetry, but we will be able to do very precise measurement. And the other one is called one gear. We can do much better, but this asymmetry is larger. But this is delta equal to 1 inference term. So with this, we will get the best information in the balance calculating. Of course, for CN gluons, we need a future EIC. We have other programs. One of these is test same model with the pattern variation. Also, this pattern variation deep analysis scaling give you unique information on nucleon structures. So the asymmetry of mirroring, you can separate into 2 terms, which correspond to 2 different coupling constants. One called C1, one called C2. It's like depends on your electron and a quark. One is axial, that is vector, or different combinations. To now, the elastic scaling like the Q weak give you information on C1, and deep elastic give you C2. So 6 GeV, we already have a first measurement done. And actually, before us selected this experiment, which is at that time a very precise experiment in the 70s, which is one of the experiments have established standard model. This is a very important experiment. But now it can do much better. If you can see the 6 GeV compared with this, we're much more precise. If you enlarge the whole scale, you can see now, together with the elastic information, we can get much better fit of the C2 and C1. But with solid, we can do another order of magnitude better. For solid, not only we want to do this, also we can cover a wide range of kinematics, help you also pin down all the corrections due to hadronic physics. But at the same time, you learn about all the nuclear structure informations, including like charge symmetry variations and some quark-gluon correlations. As well, I mentioned also one of the long-standing problem of D over U at large X. So this is the plot of what you will see from 6 GeV now with solid, another order of magnitude better. And they can access new physics at a scale of 10 TeV or so. This actually the size larger means your access physics is bigger. So you can at 10 TeV level, it's complementary to HC physics. Hadronic physics-wise, I just choose one example of this DOE at large X. Because most of the experiment to get D and U, you need a proton and neutron target. People have to use either neutron or helium-3. And JLab has two very nice experiments to cleverly try to minimize this nuclear effect. The uncertainty are often caused by nuclear physics effect. By doing the pegging bonus experiment or by doing tritium helium-3 super ratio. But this parity experiment is just use proton without any nuclear target. You can separate U and D get a ratio. That's the beauty of this proton PDIS experiment. Okay, the other approved physics is GSI with 12 GeV. We just passed the threshold. You can produce GSI, but the cross section there is really low. So that's why you need high luminosity together with large acceptance. Turn out this is a unique opportunity we have. The physics you get near threshold is very important to understand this how gluon dynamics works. In particular, some of the gluon dynamics relate to the total mass budget. One of the terms relate to the trace anomaly. But I'm not going to go into detail about this physics, but just give you how well we can do it. The earliest SLAC data near the threshold, they just don't have the perceptions. And they give you some hint that what you have, it could be due to 2 gluon or 3 gluon interactions. And if you talk to Stanislavski, he will think with this you can get all kinds of exciting conclusions. But it's clear the precision is not good there, and we need a very high precision measurement to tell you, pin down what's the threshold behavior. So this is this experiment will do. I want to show you the still ongoing study. If we can do any GPDs, there is one time-like DVCS. I just submitted to PSC, but this is one group proposal, so will be reviewed by the solid collaboration in the next just a week from now. Also, there's a very luminosity Henry process, double DVCS. You heard talk on Monday about this, and Alexander Camazon is collaborator. Submitted a letter of intent. They still continue their study, and this will be hopefully can give us a very initial first information on how you go away from the bridge TPD will work. Okay, the other one which Hong and Yi and his collaborator are working on is to study DVCS with transverse polarized helium-3. That's also the unique opportunity with solid we can do. so it can take all the luminosity of a helium 3 and take and produce. And with transverse part target, again, it's luminosity hungry, so this one is a very nice experiment for that, but it has not finished, it's still being worked on. And during our solid collaboration meeting, JLab also made a presentation of future possibility to study a very special particular example of deep virtual neutral metal productions. Probably in another year, you will see a lot more physics coming. Okay, so I gave you all the physics. I just gave you a few slides about what's the status. We started 5 years ago to propose all the experiment, try to design the device, and it went very well. We get the physics, a big program approved. And we started work on it with the support of the lab management. We try to request this Clio, officially request this and get approved. So we are, our engineers went to site visit, planning how to transfer the magnets to here. And then we also work on all detailed simulations to finalize our design of what the detector we need and what kind of DAQ system. And this is continually being worked on. We have a first preliminary CDR, PCDR, has been submitted last year, and we had a direct review, and we mentioned the direct review. So we'll continue this work until we get the PCDR to some final form of TDR and prepare a proposal to DOE for we need the money for that. Also, you heard the long-range plan, this be a potential MIE, so we work hard on that. Direct review in February was quite successful, and this is the summary of the executive summary of the report. And the committee is happy with the material presented and set up the project, and they're especially quite impressed with the international contributions. And they felt the project is in a good state to move forward, but also they identifies a lot of areas we need to continue to do more work. So these are all the components. We have the detectors with 2 different configurations. And I'm not going to have time to go through the details. And we need a lot more people working on. We have a very nice team of physicists and young doing all simulations, designs. So these are the subsystems. We have, I already mentioned the collaboration is quite strong collaboration, also with a lot of Chinese join their plan to make major contributions. We really want to welcome new collaborators if anybody is interested to join. This is a big project. Okay, I gave you a flavor of what this site is. I also want to mention when the program for the S-Phoenix and they can be first detect for future GIC. This is very easily be the first detect for future GIC. There's an initial study. So then did some study this, of course you didn't make modifications, but this will be a very nice thing for that. Okay, thank you.
Give a minute for a couple questions.
As pointed out by Matthias, JLab X range is the best for studies of color forces and iron twists. So with your terrific statistics, you should be able to measure Q-square dependence of observables. Like there are observables where you have only observable where you have iron twist as a correction. So are there any plans to measure these Q-square dependencies?
First, let me start with the one which Matthias mentioned, is D2. And D2, there is a proposal in House C for 12 GeV, but only with K-square about 5 GeV, one narrow range. And we looked at with solid data, when we take the longitudinal data transfers together, just parasitically, we will be able to cover from about 2 to 3 GeV all the way to 5, 6 GeV K-square range of the D2 evolution of chains with very high precision. It will be systematic dominance instead of statistical dominance. But also, there are a number of, even for TMDs, there's a high twist TMDs, which again, we started with our leading twist proposal first. Many of these you can get parasitically or maybe need some dedicated effort too. Certainly we'll welcome, work together to get more.
So I have a correlated question. I mean, whether we like it or not, solid is going to be a second generation experiment. So I think somewhere it has to be emphasized more like not what things can be done with solids. And yeah, I can measure G2, but what kind of things are unique with solids? And in the context of that, I also put a warning on D over U without nuclear effects. I'm turn the clock 6 or 7 years from now. We have W plus W minus data from Firmament without nuclear corrections. We hopefully will have bonus. We hopefully will have tritium. I think somewhere you guys have to think about not just what can be done, but what kind of things are unique for a second generation experiment. So that might mean that some of your most favorite plots you might not want to show it.
Yeah, it's a good point. We have several things unique. The peptide itself is unique, and the polarized proton, neutron proton is a possibility. Class 12 have this HD, but we, in the kinematics we can do, we have about one. Actually, in general we have 2 orders, but for polarized protons we have about 1 order of magnitude more. In the kinematics, we can do classical a little larger in angle. For the neutron, of course, it's very unique. We are about 2 orders more than the earlier small solid angle experiments, so big light experiment. This gives you, we can do really multi-dimensional. This is very unique. If you look at the projections like the other ones, you cannot even do the pre-velocity, for example. It's just impossible with the precision. The other thing I want to mention, this one compared with some of the like so big light others, is the 2-phi complete coverage makes it very nice for, especially for this asymmetry. We can do double asymmetry to really cancel a lot of systematics. As soon as we reach the statistics precision, we will be systematic dominant. This one is really nice to have this already during our proposal discussion, and this is in a very nice feature. You don't need to spin flip your target. You already be able to get the angle modulation. But by flip spin, you get cancellation of systematics. GSI, this is almost no competition. So the people look at how well you can do it. That's, but it's again all magnitude difference. So you're right. We need to produce this comparison plots. We've been focused on not. This was not our initial focus to produce comparison, just to see what we can do. But you're right. We should produce these ones.
Okay, thank you, Jyoti. Next on the schedule is a coffee break, so we're running a few minutes behind, so let's come back at 3:50.
Talk about just a brief overview of the approved experiments that we have coming up in Hall D. Give a brief update on the status and our commissioning, and take an early look at some physics data. So our flagship experiment is the GlueX experiment, where we're searching for hybrid mesons. These are mesons in resonances that exhibit gluonic field excitations. So they have the gluon, one of the gluons behaves as if it's a constituent particle in the system. So there's a large spectrum of these states predicted, but so far there's only strong evidence for one of them, the pi 1 state. So if we can measure the spectrum of these states, we will provide access to the gluonic degrees of freedom in the confinement regime. So it's really important to measure these states. Now it's very difficult to do. However, some of them have exotic quantum numbers that can't arise from a valence QQ bar alone. So if you can detect one of these states, like for example pi 1 minus plus, then it would be an unambiguous signal that you have some kind of exotic state. So here's a prediction from Joe Dudek and company at associated with Jefferson Lab. Lattice QCD, the spectrum of mesons. Here they're using a mass decline at 390 MeV. So you have the ground states, the pseudoscalar mesons, vector mesons down here, the large spectrum of excited states, and the ones that are in these gold boxes are predicted to be the lightest hybrid states that contain these, that contain a valence gluon. So most of the experimental evidence so far has been for this pi 1 minus plus. So I should mention these states are grouped by parity, so the negative parity states, positive parity states, and then on the right are the exotics, these states that can't be a simple QQ bar system. So what we want to try to do is map the full spectrum of these states if possible. So far there have been several experiments that have searched for them, most notably Compass, E852, and VESS. What I'm showing here is evidence for the pi 1 1600 from the E852 experiment back in 2001. Here the pi 1 is the dominant signal, and they also, this is in reaction to pion beam on a proton with pi minus eta prime final state particles. So as a function of the invariant mass, the eta prime and pi minus, they see a very strong P plus wave, which they think might be the pi 1, A2 and A4, and then when they take the phase difference of these resonances, they see some strong behavior here, which is indicative that they might indeed have found a resonance. So, but again, most of the evidence is for this one state, and what you want to do is measure the whole spectrum. That's what the GlueX experiment has been designed to do. We have a linearly polarized photon beam incident on the liquid hydrogen target. And the advantage of the photon beam is that spin 1 photons are more favorable for producing some of these hybrids than, say, a spin 0 pion beam. We're not the only game in town. Other experiments are looking for these as well, such as the class here at Jefferson Lab, both in the 6 GeV and the 12 GeV era. And some of these are upcoming as well. But this is a topic that's being looked at by many collaborations around the world. But this isn't the only experiment that we're running. We have the charged pion polarizability experiment. It's going to run where they try to measure this alpha minus beta for the pion, where these are electric and magnetic polarizabilities. And by measuring this, we'll be able to test the even parity parts of the chiral Lagrangian, because they're related to the charged pion form factors of A and B. And so over here on the left is the plot of some of the previous measurements for the polarizability. Here's a point from the Compass talk that was yesterday morning, where they looked at it in the pion beam. But here, we're going to look at it through the Primakov process with the photon beam interacting with the nucleon Coulomb field. And so we hope with this experiment to have much smaller error bars and to help reduce the uncertainty in the standard model predictions of the anomalous magnetic moment, GMU minus 202. So, but in order to do this measurement, we have to measure the cross-section of this process down to 50% level. If you want more details on the charged pion polarizability, refer you to the Compass talk yesterday. Another experiment we have is the eta decay width experiment. The main purpose of this is to try to determine the light port mass ratio in the most model way. So there are some different model predictions of what this port mass ratio is, and previous experiments, and the proposed experiment is designed to, well, the actual experiments that run, is designed to help improve distinguishing between these different model predictions. But in addition to that, it will also help us improve our understanding of the eta prime mixing table, and it will help improve all extraction of all widths in this eta decays by a factor of 2. All right, so the GLUEX collaboration is made up of about 110 members, 21 different institutions, the Jefferson Lab and many others in the United States. But in addition to that, we have groups, universities in Canada, Chile, Armenia, Greece, Russia, and the United Kingdom. So it's a pretty international collaboration, and we have other groups are applying to join as well. This is a picture of this is a drawing of the GLUEX detector. So we have the electron beam from CBAF is incident on a diamond wafer, where we produce a photon beam that goes into the main detector. The electron beam is tagged to determine the photon beam energy, and then the photon beam is incident on the liquid hydrogen target, and around it we have a series of detectors to measure the particles, such as the drift chambers, calorimeters, etc. So our schedule is, we're doing commissioning now in opportunistic physics when we can get it, until spring of next year. And first physics will be in the fall of 2016, and full intensity running will be 2017 onwards. So this is a picture of our beam line. So here the beam is coming in from CBAF on the left side. There's the diamond radiator and the electrons that are scattered are bent by this Tagger magnet into the Tagger photoscope and microscope to measure those electrons. The beam then travels a long distance before it gets into the hall. First, we have a collimator to try to collimate the beam. So this is the tagged photon spectrum, but the collimator helps enhance the polarized part of the distribution. So then we have the triplet polarimeter, air spectrometer, and then it finally goes into the detector hall. The design is to have the coherent peak be at 8.49 GeV. We expect to have a polarization of about 40% in that region. So here's the pictures of most of our baseline detectors. They're all installed and working. This is our central drift chamber. It's around the target. The SAR counter is directly around the target. The central drift chamber around that. Barrel calorimeter is around that, and those are all within the solenoid magnet. And then as you get going towards forward angles, you have forward drift chambers, forward calorimeter, and forward time of flight plane. So these have all been built, installed, and are working. This is our spokesperson, Curtis Meyer, in his natural habitat. This is the Hall D. The beam is coming in from the back here, going along this way. The solenoid magnet inside of here is the forward drift chambers, barrel calorimeter, etc. And then further over here we have the forward time of flight. This is the dark room that's around our forward calorimeter. But in addition to these, we also are in the process of building a focusing dirt detector. So we're using 48 of the bar dirt quartz bars that are going to be used to separate pions and kaons up to 4 GeV in energy. So this is a work in progress and will be installed in fiscal year 2018. So fall commissioning, we had about, once the beam was tuned onto the target, we had about 18 integrated days of beam. About 10 GeV of beam, a wide range of currents, with a solenoid field of about 1200 amps typically, and a thin plastic target for that. So our primary goals were to commission the beam line, which is a huge success, trying to get the beam tuned to the tagger and the target, active collimator, air spectrometer, etc. Through all these systems onto the target. That was a huge success. Also, though, we wanted to check out and make sure that all the equipment is working. We're record data, the data acquisition work, the trigger was working, all the detector. And in addition to those things, we wanted to collect data for preliminary detector calibration and alignment, and that was all a success. So here's a reconstructed event this is from our online system. So this was all done online very quickly after we got beamed. Here we have, this is our side view of the detector, central drift chambers, and you see tracks that are going forwards and are being reconstructed. They're hits in the different detector systems. This is an end-on view where you can see the tracks are curling and there's hits, and they're associated with showers, the barrel calorimeter, star counter, etc. So all the detectors are working, all the hits are correlating with each other, and everything's going well. This is a different event, but again, it's a similar thing. Curling tracks reconstructed in the central drift chambers, forward tracks, and here I'm showing this track is making a hit in the forward calorimeter, and it's showing hits in the time of flight. So this is just in the first few days of getting beamed, showing that all of our detector systems are working. Our reconstruction is working. So we had full detector running for a couple of weeks at 1200 amps. We were able to record data from all subsystems. We were able to show signal coincidence and hit correlation between the detectors. I didn't show this plot, but we also reconstructed the target position for tracking, and we were able to do particle ID. So here's electron-pion separation using the shower energy relative to the track momentum in our forward calorimeter. This is proton-pion separation from timing, and this is, again, proton-pion separation, this time from energy loss. So our calibrations are still a work in progress, but everything is going well so far. So then for the spring running, again, the plan was to run for 2 months at 10.5 GeV beam. One was opportunistic, but one dedicated. However, we only, due to several problems, we only had 10 solid days available. It's cut short due to mechanical problems, mainly with the liquid coolers. So the plan was to run 1300 amps, but this time with the liquid hydrogen target. Last time we just had the plastic target. Beam energy half, 5.5 GeV over wide range of currents. So we had a lot of successes, even though we had the beam for 10 days. We were able to commission the target, goniometer and diamonds. We did a lot of optimization of our DACs and triggers, and we were able to collect some data for further calibrations. And the active collimator fast feedback is a work in progress, but it's going well so far. They were able to get the 60 hertz noise away, so that worked really well. But we wanted to establish a solenoid running at 1300 amps, and unfortunately we got a quench. So just a little bit more about the solenoid status. It was built at SLAC in the early 1970s and was used at SLAC and Los Alamos, but it never quenched. It was considered cryostable at 1500 amps, and over the period of several years, it underwent multiple repairs at Indiana and Jefferson Lab. Since we got it here, and built it, installed it, and everything, we've operated the magnet at many different currents. First, we just did it for 10 minutes just to see if it was working at 1500 amps like it was designed to do. Then later on, we ran it for several hours at 1350 amps. Ran it for 4 days, 1300 a day in 2015. And then 1200 in the fall running, we had about 2 weeks worth at 1200 amps over the course of some time. However, the magnet has had, during this time, it's had 2 quenches. First at 1460 amps while it was ramping up in 2015, and then again at 1300 amps after 22 hours in early May, late April. So, so far we haven't found any damage with the magnet. We're not quite sure why it's quenching. So we've completed some low current tests and everything looks fine. And so now we're undergoing some high current testing, and we need to optimize the current for efficient running for the rest of the experiment. So here's a plot of the reconstructed event vertex. So you can see our 30 centimeter hydrogen target is reconstructed. You can see our vacuum chamber exit window, and the solid plastic target we had just a little downstream. So our vent reconstruction, track reconstruction is working. When you look at the XY plane, you can see some centered on where the beam is, and you see some hits in the start plan, etc. So that's all good. One of the big landmarks of this run was we were able to commission our goniometer diamonds. So this right here is an instrument where the diamond is mounted here, and the cross is showing where the beam is impinging on the diamond. And so what we're able to do is we're able to rotate the orientation and pitch and yaw, and by doing the rotations, we're able to change the energy of the coherence peak. So this is a normalized spectrum of the photon beam energy. So we're able to change the position of this as well as try to maximize the polarization of the beam. So for example, when you're trying to find the optimal angles to run at, you can rotate along the surface of, for example, a 2-degree cone, and you sweep out a space. This is pitch and yaw, and the radial axis is beam energy. So as you can see, as you rotate, you're scanning different. The coherent peak is the most intense part of the spectrum. So based on how you angle the diamond, you can change the energy of the coherent peak. And the symmetries in the plot are due to different lattice planes in the diamond. One of the other things we've been able to do is we've got a robust system of reconstruction monitoring, so both online and offline. So not only can we see in the counting house how the reconstruction is working, but offline what we're doing is we've been tracking how our data looks as calibrations improve. So what we do is we run bi-weekly monitoring lunches where we submit a whole bunch of jobs over all of our runs, and we perform full reconstruction, and we track we track the resolutions and the timings of different detectors. We track just also our software to see how our success rate is, CPU and RAM usage, how it's scaling for cores, etc. And what we can do is we can web browse. All of these plots are available on the web. Here's a screenshot showing this is photon invariant mass, different bins of cluster energy. So this is all available on the web, and people can see the whole history for many different runs, many plots for many different systems. You can even browse the root files themselves online or download them. And then in addition to all those things, while we're running this, we're also saving our reconstructed data to disk so that users can do the physics analysis. So let's take an early look at some of our physics data. We've done a lot of bump hunting. So if you look at this is the spring data, proton target to proton gamma final state. You look at the invariant mass of the photon pair, you see a very strong pi0 peak. And if you zoom in and rebin in this area, you can see the eta peak as well. I should mention that we're still calibrating our pi0 width, but right now it's down to about 10 MeV for photons in the barrel calorimeter and 12 MeV for the forward calorimeter. So we want to knock those down a little bit, but things still early and things are going well so far. In addition to that, we see strangeness. This is lambda events from their decays to proton pi minus, and K shorts from their decays to pi plus pi minus. And to select these events, we had to cut on the attached vertex. So our track reconstruction is working well enough to extract those. And then a few other peaks. Here we have omega knots. So pi plus, pi minus, pi0. Look at the invariant mass of that system, and you see a strong omega peak. Pi plus, pi minus, you see a strong rho peak. And then K plus, K minus, you see a strong phi peak. Now we don't have direct kaon ID yet. So this is just, we cut away the protons and we assign all the particles to the kaon mass. So here's our pi background where it's been assigned to the wrong particle. But we still see the strong phi peak. So it's all going on. And finally, with the spring data, since we have a polarized beam, we can look at asymmetries. So this is gamma p goes to rho, P, for the rho decays into the pi system. And you can look at the angle of the rho decay plane with respect to the photon beam polarization plane, plot your events. And so this is a spectrum that we get blue points, or if we just have the amorphous radiator, so no diamond, no beam polarization. If we have the diamond in, we have a nice asymmetry. So this actually matches the previously published world data at this particular energy. So with only about 3 hours of beam. This is actually fast turnaround on this analysis. We were able to get that done with only 2 days after the turnaround. So everything's going well and smoothly. We're able to turn around the data quickly. So to summarize, all physics, we have a rich program that is going to last us many years. In addition to mapping the hybrid meson spectrum, you can also map excited baryon spectrum, which I didn't really spend much time talking about. But look at the charge pion polarizability, look through some data studies, look at the decay widths, data dynamics, etc. We're commissioning and opportunistic physics from now until spring of next year. First physics will be in that fall, and then full intensity running from 2017 on. So we're eager for more beam, and the main thing we need to do is finalize calibrations and get started on other physics analysis. Thank you.
Two questions. First of all, can you say anything about what the luminosity limitation is, or if the rate limitations that you saw on this limited set of data are consistent with what the expectations were? I'm interested, of course, in the ramp up to 10 to the 8th, the 1 times 10 to the 8th photons per second in the near future. So what can you say about that?
I'll defer to Eugene.
So we were below even the first stage of fluids, which is 10 to the 7th,
right,
something like that. So at the moment we're limited mostly by the DAQ. However, it is gradually improving, and so we're at the end of the run, this spring run, we were able to run for a few minutes at 30 kilohertz, which is about enough to cover our first stage. But then it crashes, so it has to be left. Still a lot of work.
So I guess the important message is it's not a detector limitation right now, as far as we can understand.
There is a detector limitation on the side of the drill changes, so we trip them a few times, but then we can afford to reduce slightly the high voltage of that because the efficiency is good enough. So we don't see, for the first stage, we don't see limitation. The second stage, we did.
The second question I have is on your 5 peak. You said that you didn't have any cuts on that, but I find that hard to believe because you should be completely spawned by time. You must have a time flight cut or something.
No, I don't think so.
Really?
We have a DEDX cut to make sure it's not protons.
Okay. But there's no time of flight cut on there to try to
It
separate?
wasn't calibrated at that point.
Okay. Thanks.
So go back to your comparison with the SLAC data. Is the SLAC data background subtracted? Why do their values go to 0 and yours not? Peaks are 80.
Polarization.
They have higher polarization. Yeah. You have about 60% in our data.
Any more questions? All right, let's take our speaker in. Next up, we'll have Juliana Lada, and we'll be giving some results from the transfer state experiment.
Let me thank the organizers for asking me to give this talk. This will be like an overview of results, all the results from the transfer city experiment that are published. until now. So I won't be spending a lot of time, but basically the transversity experiment was proposed to do a semi-inclusive deep inelastic scattering on helium-3 target to study the, initially the motivation was to do this Collins and Sievert's moments on the neutron. So in the semi-inclusive deep inelastic scattering, unlike the inclusive DIS, we get more information from detecting the outgoing hadron in coincidence with the lepton. So by tagging the flavor, one can study the stuck quark flavor and the dependence and the transverse momentum dependence of the stuck quark. So, the whole range of correlations can be studied in this fashion, and this gives us a three-dimensional picture of the nuclear in the momentum space. So the cross-section of the series boils down to, in the leading twist, these terms here. So you might have seen most of these previously, but one can categorize these into accessible in the unpolarized beam and target, and the polarized target and polarized beam and target. So if you have a polarized target, either transversely or longitudinally, you can access these four. So for transversity experiment, the target was transversely polarized, and the beam was longitudinally polarized. So one can access all four of these EMDs, the Sieverts, Wong-Gear, G1T, and transversity, and the velocity. So here is an overview of the experiment. Basically, the experiment ran from October 2008 to January 2009. The beam energy was almost 6 GeV, it was 5.9, and the beam was polarized, and the flip rate was 30 Hz. And the target had two different polarization directions. One was transverse in plane to the lepton, in the lepton plane, and vertically with respect to the lepton. So there were two transverse directions. The polarization of the beam was 60%. I'm sorry, this is the polarization of target, which was 60%, and the flip rate of the target was every 20 minutes. And the data was collected in both coincidence mode by detecting the scattered electron in the big bite spectrometer and the hadron in the high resolution spectrometer. We measured both pions and kaons, the charged pions and kaons. And HRS had a both rich detector, and we had time of flight method to detect the particle ID. And we did both single and double spin asymmetries on this experiment. So you have seen this slide before. Basically, we have, when you have unpolarized target and transversely polarized, unpolarized beam and a transversely polarized target, you can get your asymmetry from the target spin, and then in the reading twist you can have three different moments, PMDs coming to the equation. So, but in order to, so each one of these modulation, each one of these PMDs have angular modulations with phi h and phi s, with phi h being the hadron plane with respect to the electron scattering plane, and phi s being the angle between the spin vector and the electron scattering plane. So, but we detect the electron in HRS in the Hall A, and electron in the big bite and the hadron in the HRS. So in order to get the full acceptance, azimuthal acceptance, we need to flip the spin of the target that way we can achieve the full azimuthal acceptance. So here I'm showing you the Collins angle phi h plus phi s with in 4 different x bins. That's how we divided our data into 4 x bins. So each of these colors basically corresponds to when you flip the spin of the target up, down, and left and right with respect to the beam direction. So that way you can cover the entire phase space of the azimuthal angle for Collins and Sieverts. For Collins, we have pretty much near complete angular coverage. For Sieverts, as we go to the higher x, we get complete azimuthal coverage. So this is a nice technique because of the limited acceptance on the detectors. So the way we did particle identification in the big bite is from the shower and pre-shower. We just had a calorimeter to do the particle identification. So this is the plot of pre-shower energy as a function of energy over momentum. You can see a nice electron peak around 1. And when we use the big bite and high resolution spectrometer, we can do a time of flight kind of technique and then identify the particles in the HRS, proton, kaons, and pi plus. We had a threshold aerogel detector in the HRS, so we could, which was detecting pions. So we could suppress all the pions when we are detecting kaons by putting a cut on the aerogel. So the kinematic coverage for the experiment was is basically shown here. Q square, when the cuts are shown here, the full range is shown here. So the Z of the haton was on an average 0.5. So that was right in the middle. So it was high enough that we are in the current fragmentation. So that compared the average Q square was 2 GeV, compared that to the Hermes Q square, which is 2.4 GeV. So these results you have already seen from previous talk. These were the first results that were published. These are the Collins and Sieverts moments for the neutron. And here, as JP mentioned earlier, we see that the data agreed with the sign and the model predictions in 2011. And for the Collins asymmetry, the one point which was much larger and negative was the Q square x of 0.35 or so. We saw pretty large asymmetry compared with others. So the recent global extraction of transversity was done by Zhang Wokang and others, and this was actually recently released in the archive. So you can see this. So for this extraction of transversity distribution, they included both all the Hermes, compass, and JLab data, including photon, neutron, and M3. And they also did the evolution here. So you can see the black dotted lines are Q squared for 2.4 GeV. That's where the whole data they extracted for, and then they evolved to higher Q squares. So as you can see, the transversity is more sensitive only in the valence region. So as you go to the lower X, the evolution actually doesn't play a big role. Anyway, so that's good to see all the JLab data is being used in the global analysis now. So the next result is velocity asymmetry. Again, this is a very tiny asymmetry that has been predicted, but our data, we had very large statistical errors, and essentially we don't see much of asymmetry on these in our uncertainties. And on top of it, velocity is suppressed by another factor, a kinematical factor, KT square or M square, which is mass of Newton. So that compared to the Sieverts moments, So any big asymmetry will be suppressed. Again, so now coming to the double spin asymmetries, this is the beam target double spin asymmetry ALT. So this is sensitive to the ALT is sensitive to the G1T, which is a Wong-Gear function, and we can see from the results, these were published in 2012. For pi plus, we see there is as we go to higher x, the asymmetry favors the negative values. But for pi minus, there's a clear non-zero asymmetry. And this shows for the first time a non-vanishing quark transversal helicity distribution, which reveals alignment of the quark spin transfers to the neutron spin direction related to the quark orbital angular momentum. So this was in 2012. So more recently, we also looked at the Collins and Sieverts asymmetry, single spin asymmetry for kaons. And this is the results published in 2014. This is for Collins, K plus and K minus, and on the bottom is the Sieverts K plus and K minus. For K minus, we didn't have a lot of data, so we had to bin all our data into one bin. But for K plus, we could do a 4-bin. So as you can see, the K minus asymmetry favors negative values, which is surprising, considering that C-quark contribution initially, we thought it could be small in the valence region, but it seems like it is something that we got us excited. But for K plus, we don't see much of an asymmetry here. But so, and this information will again go along with the Hermes and Compass data in the global analysis of to extract the C-quark PMDs, or Sieverts and transverse. So now, those are the data that I presented until now were from the semi-inclusive deep inelastic scattering. Now there's another channel we looked at is the inclusive hadron production, where you just scatter electron off nucleon and helium-3 and detect the outgoing hadron. So you just detect the outgoing hadron, so you have no information about your electron, so no Q square. So the only scale here is the PT of the outgoing hadron, which is the hard scale for this process. So you have to understand this process, you have to have hard enough PT or a hard enough scale of the PT has to be large to actually get access to the information that is in the coming from the quarks. So the relevant kinematics here is PT and Feynman X instead of Jordan X. So assuming the TMD factorization is valid in the inclusive hadron production, Anselmino and others predicted that Sieverts' contribution to this process dominates, and Collins' contribution is negligible. So the asymmetry itself shows up as a sine phi s moment. The phi s being the spin angle of the angle between this scattered plane and the spin of the nucleon. So we looked at this asymmetry, and this is for the before we looked at the asymmetry, we did a systematic check to see when phi s goes to 0, the asymmetry should go to 0 since the modulation is sine phi s. So this is from the data from when the spin angle was 0, and you can see for pi plus and pi minus the data is 0 at the level of 0.1%. So when we look at the vertical spin, phi s equal to 90, the asymmetries are non-zero and clearly in opposite sign for pi plus and pi minus, and K plus asymmetry has the same sign of pi plus, but with much larger magnitude. For proton, very small asymmetry, but For K minus, the error bars are large, so we can't tell whether it is actually positive or negative. So this process is more similar to the inclusive hadron production in the PP collisions or any hadronic collisions. So you have a transversely polarized proton, you hit with another proton which is unpolarized, and you look at outgoing hadron. And if you remember the E706 experiment from JLab, they see a pretty large asymmetries up to 40%. So one can, so what I did is here, these asymmetries, these pi plus and pi minus, looked at the function of PT. You can see here, although PT range is pretty small, just from the HRS, you can see clear non-zero asymmetries arising as a function of PT. This for the helium-3. So from helium-3, we extract the neutron asymmetries by correcting the dilations and stuff like that. And this is the final neutron asymmetries for it's called AN for pi plus and pi minus. And the bottom subplot is the range of XF. So there are no theoretical predictions because it's hard to get prediction at a low PT value. Typically, all the predictions are done at a PT greater than 1 GeV. But the data agrees with the sign of, so there are predictions above 1 GeV, but these data agrees in sign with those predictions, but they can't actually predict the magnitude. So this was published in 2014. So that was single spin asymmetry in inclusive hadron production. And you look at the double spin asymmetry in inclusive hadron production, the same process. Now we look at the double spin asymmetry where electron, we consider the electron spin too. And here the ALT comes in as a cosine phi s modulation. So why is ALT interesting? Because ALT is in inclusive hadron is a subleading twist, which is a twist 3 observable in collinear factorization. So this is more like a collinear twist 3 function, and the contributions can come from both the distribution and fragmentation side. So this is something called a G tilde x, which is a collinear twist 3 Wongier type function. So one can study this function, which is sensitive to this asymmetry. So what we can learn is basically the gluon-quark correlations within the nucleon, which is coming from the distribution side, and also in the fragmentation side, where you have twist 3 effects in the fragmentation side. So we looked at this asymmetry, and here I'm showing you the helium-3 asymmetries for charged hadrons. The hadrons are on the x-axis here, and you can see because it is a cos phi s modulation, all the asymmetries for phi s equal to 90 and 270 are pretty much 0, and as phi s goes to 0 degrees and 90 degrees, start to say non-zero asymmetries. And this is again a PT distribution of the same asymmetry for pi plus and pi minus in all these 4 cases. So phi s is 90 for pi plus and pi minus, 270 here, and 0 and 180. So only the bottom 4 has non-zero asymmetries as a function of PT. So when you combine that and plot divided into 3 pins as a function of PT, you can see this is for pi plus on the bottom and pi minus on the top. This is helium-3 asymmetry, and we extract the neutron asymmetry. Again, you can see the final plot. So basically, a clear non-zero asymmetry is observed, and the models that the predictions that were done were coming from 2 different types of approximations. One in which they assume this twist-tree collinear TMD is using a Wilczek, 1-0 Wilczek type approximation, and that agrees with the sign of the data. And in the second case, they assume that this is equal to the Sieverts type asymmetries. In that case, the predictions doesn't agree at all, and even it has the opposite sign. For example, you can see pi minus Sieverts as an opposite sign to the data. So pi minus Sieverts, the red color is here, and the data is here. Anyway, so those are the predictions from this publication here, and the results were published. Results are under review in Physical Review C, and most likely will be published very soon. So, so the last reaction that I want to show is the target single spin asymmetry inclusive DIS reaction, which gives AY. So this is the data came from the transversity experiment, but the experiment itself had a different number. So this was considered a different experiment. So basically, what we are looking here is AY, which has a sign bias modulation. It's an inclusive DIS reaction standard with a transversely polarized target, and the asymmetry comes from the two-photon exchange. So in the one-photon exchange at Born level, due to time reversal invariance, basically this asymmetry is 0. But when you have two-photon exchange, one-photon and two-photon exchange interference terms, this asymmetry can be large. So there were two model predictions for these two-photon exchange contributions to AY. One coming from Andrea Afenesser, in which he assumed that the two photons are exchanged with a single quark inside the nucleon. And the second, in which the predicted asymmetry for that particular case was 10 to the minus 4 at around x equal to 0.3 and q square, which is the transversity experiment's kinematic range. And the second case was done by Andrea Matz and Mark Schilliger, in which he assumed that the two photons exchange with two different quarks, one with the stuck quark and the other with the quark-back-quark spectator system. So in that case, the asymmetry can be quite large, 10 to the minus 2. And currently, before we published our data, the Hermes proton data looked at this channel, and then their data was consistent with 0 within 10 to the minus 3 level, and that was what I told. And here's the data, the final results for the AY on neutron from the inclusive DIS data. The data was collected from singles trigger in the big byte and HRS. So the black points are the ones from the big byte, and the red point here is from the HRS. And red point here contains both systematics and statistics. And the black points have only statistical error bars. The systematics are on the bottom. And the blue point here is the average of all the data which are above a W greater than 2. So this is the average of all these 4 points. So you can clearly see this is the first non-zero measurement of AY on neutron, and it is consistent with using the Sieverts input. So the model prediction, again here, there are two different inputs. One is the Sieverts and another one is a multi-part. So to summarize, the summary of all the results, the published results from 2011 to 2015, these are about 7 results. The first 3 are physical letters, and the rest of them are Physical Review C. The last one is under still review, and hopefully will be published very soon. we still have a few ongoing analysis. One is on the unpolarized Celis cross-section, which is done by Shefei Yan from Duke University. We also want to look at the double spin asymmetry in the inclusive DIS to extract the G2 on the helium-3, which will be done by the Lucia Zhao and Stone group. So overall, we had a very productive analysis and a lot of results. So this is the whole collaboration, and the highlighted people are spokespersons, students, and postdocs. So let me summarize. So our experiment was very successful. This was the first experiment to measure the targets in spin asymmetry and the double spin asymmetry in semi-inclusive deep elastic scattering, and also inclusive hadron collection channels contrast with polarized helium-3 target. So we explored very rich EMD physics at JLab using polarized helium-3 with many results published and 3 more ongoing. There were 9 PhD students, including 2 who joined after the experiment, a total of 7 publications. And I think these results laid a pretty strong foundation for the future precision study of EMDs in EM3 and JLab.
Any questions? So last but not least, Vince Sokolsky will give the talk on measurement of double polarization asymmetries in the quasi-elastic region.
All right, I'd like to thank the organizers for inviting me to give this talk, and thank all of you that have stayed here to hear the last talk. All right, so today what I'm going to talk about is using light nuclei as effective neutron targets. In particular, I'm going to be talking about the free-body system of helium-3, and then I will go through the experimental overview for the experiment that I'm discussing, and talk about the complicated acceptance averaging procedure that was used for the theoretical calculations. And then I'll show you the new results for the double polarization asymmetries before summarizing and concluding. All right, so light nuclei. So for the proton, we know its properties and it's been extensively measured. So, we think we have a reasonable understanding of the proton. When it comes to the neutron, we're definitely not at the same comparison level as the proton, especially in terms of the accuracy of the charge magnetization and spin information. And the main reason this comes about is that we don't have a free neutron target. So direct measurements are not possible, at least not easily, at least in terms of wanting to get the statistical precision. So the solution is we do indirect measurements using the appropriate target. The first of which is the deuteron, which is a proton-neutron system. And then we have free body systems such as helium-3, which are 2 protons and a neutron. There's also tritium, which is, of course, the mirror nuclei of helium-3. But to get the neutron information from these targets, we need to have detailed knowledge of the structure of light nuclei, which is crucial in terms of extracting the neutron information from these light nuclei. And for this talk, I'm going to be focusing on helium-3 as an effective polarized neutron target. So why study helium-3? Well, it's interesting because it is a calculable nuclear system where theoretical predictions of the nuclear structure can be compared to data with increasingly accurate, with increasing accuracy. And one of the main goals of this study is that we need to understand the helium-3 ground state spin structure because we typically have used helium-3 to extract neutron information on electric magnetic form factors and then the spin structure information such as A1N, and the two structure functions G1 and G2. So theoretically, what has been predicted is those three main components to the helium-3 ground state wave function, and the knowledge of the smaller components of the wave function help us to understand the standard model of the two-body system in terms of what we understand of helium-3. But to have a good understanding of this, you have to understand all the reaction mechanisms of what you're actually measuring. So you need to know the ground state of helium-3, which of course you cannot measure directly. You have to include final state interactions, meson exchange currents, and finally you have 2 nucleon and 3 nucleon forces that you also have to build into your calculation to adequately describe helium-3. So if you look at polarized helium-3, and if you just look at the magnetic moment, or the ratio of the magnetic moment of helium-3 to the neutron, it's approximately 1, at least within 10%, which is one reason we typically say that polarized helium-3 is an effective polarized neutron target. Because essentially, because the wave function is dominated by the S state, about 90% of it, so when you polarize it, you will essentially have a polarized neutron, which is effectively what the magnetic moments is also telling you. However, there is a D state, and there's also S prime state, which is a big symmetry state in terms of spin, isospin, and space correlations. And so these have been calculated, and these are some of the calculations using the different potentials. There's also a very small contribution from a P state, but in terms of the other ones, it's expected to be significantly smaller. And then it has been calculated that the polarization of the neutron, or at least the effective polarization of the neutron in helium-3, is about 86%, and the proton has a small negative polarization, or the protons have a small negative polarization. If you consider the deuteron, there's an analog to this. So the vector polarized deuterium, you have measurement of E pi P knockout, measured versus P miss. At low P miss, it's dominated pretty much by the S state, and you have the theoretical calculations here for playing with impulse approximation, having the S state and the D state turned on. So with the deuteron, you have the S state and D state. And what you see is as you go above the Fermi momentum, the asymmetry starts to change and actually flips on, which indicates the importance of the D state as you increase above the Fermi momentum. So you could expect something similar in terms of helium-3, that as you go to increasing P miss, or the momentum of your reactive deuteron, if you do E prime D knockout, that you would have some other, or some sensitivity in terms of the asymmetry to also see this. If you look at the true ground state of helium-3, at least from the calculation from about 30 years ago, this is the gory details of all that information. So before the experiment ran, and we even got updated calculations as the analysis proceeded. So we have state-of-the-art calculations. We have 2 full Faddeev calculations, one from the Bachmann group and one from the Hanover group. And this lists the nucleon potentials that are used, what they did in terms of 3 nucleon forces, and how they treated the final state interactions and meson exchange currents. The Hanover-Lisbon group also have some degrees of freedom, including the delta isobar, and they also include Coulomb interactions. The PISA calculation is not a Faddeev calculation, but it is expected that its accuracy should be equivalent to those of the Faddeev calculations. We were also expecting some calculations from Frencho, but it's at this point not clear if we're going to get those calculations like this. All right. So if you look at the differential cross-section for E prime B knockout, or you do E prime P knockout, the differential cross-section can be broken up into different pieces in terms of unpolarized, or if you have a polarized target, or a polarized beam, or a combination. In our case, we have a polarized electron and a polarized target, and so the combination that we're interested in is this asymmetry here. In particular, the calculations are with respect to the Q vector. So AZ is parallel to the Q vector direction, and AX is perpendicular to the Q vector direction. So it's a difference in terms of your target orientation and your target orientation, and the direction of the helicity of the electron beam is how you get these asymmetries. And this shows you the expected precision that was when the experiment was proposed. And these are the different theoretical calculations from the three groups that we have. And at the time, as you change PMIS, you see that there was actually substantial differences between the calculations. So this would give us an idea of the dynamics of what goes into these calculations. And once we have the data, we can do the comparison to these and try and understand how well do we really understand the helium-3. At the time of the calculations, the theorists were also willing to essentially turn on and off the different components for the helium-3 wave function in terms of if you have only an S state or S and S prime, S and D. And you can see as you look at the two different asymmetries, depending on what components are actually included, you have some sensitivity of the size of the asymmetry, to those different components. So, though since that point in time, because turning these different components off is not Lorentz invariant, the theorists don't actually like us to do this, or do not like to actually do this anymore. But it does show you that you have sensitivity to the different components of the wave function. So this shows you the experimental setup. It ran in Hall A a few years ago. The electron beam is coming in from this direction, longitudinally polarized, with the polarized helium-3 target in the center. The target polarization was polarized either parallel or perpendicular to the beamline direction. And the electrons were detected into the one high-resolution spectrometer here. And then the recoil of deuterons and protons were detected in the big bite spectrometer, which is shown here. We had a beam energy of about 2.4 GeV. We had two different angles for the electron scattering of 12.5 and 14.5 degrees. And also two different angles for the big bite the big bite angle detection. And so we actually have two Q-squared measurements on average about a quarter of a GeV squared and 0.35 GeV squared. So in terms of the performance of the helium-3 target, this is actually after the updates of using hybrid alkali polarization and narrow bandwidth lasers. And so the average polarization from all these developments we had for this experiment was about 53%. Though you do see in the longitudinal configuration, we were actually closer to about 58% versus the transverse because of or efficiencies of polarizing. So the big bite spectrometer, for this experiment, we used what we refer to as the hadron package to detect the protons and neutrons. There were two planes of wire chambers that we used for track reconstruction. And then we had two scintillator planes that we refer to as the DE and the E plane that we use for particle identification and energy determination of the energy deposited by the deuterons and the protons. So in terms of separating the protons and deuterons in the data, this shows you the energy deposition in the thin scintillator versus the energy deposition in the thicker scintillator. So we have a lot of protons, and you can see the strong proton band here. And this also shows the deuterons. To do a better separation of the deuterons, if we plot the total energy deposition versus the particle momentum, we now have a much cleaner separation of deuterons and protons. So compared to the amount of protons we had, we got about 1 to 2% deuterons for all the protons. And once we make this cut, the contamination of the leftover protons in the deuteron sample is 1 to 3% depending on the momentum of the recoil particle. As you go to higher momentum, the contamination is less. Now, so that shows you the separation of protons and deuterons. Now, if you look at the acceptance of the high-resolution spectrometer in terms of the scattered electron energy versus the angle, this is what you see in terms of those two. And we have the calculations for the different groups. But because of the intense or the numerical intense calculations, they cannot provide us very fine calculation, at least over our acceptance. So the three groups first provided us calculations over a grid of about 36 discrete points. And then the Hanover-Lisbon group gave us a finer grid of about 63 discrete points. However, that's still, in terms of comparing the theory to the data, because you have the entire acceptance or at this, for this, you cannot easily do a direct comparison. So you have E prime and theta, but on top of that, you also have the spin angle, and you also have the azimuthal angle of the detected deuteron, and you also have the P miss, or the missing momentum, that you also have to average over. So you have essentially an average over a four-dimensional space. And so if you look at those discrete points where the theory is calculated, of E prime versus theta, and you look at the deviation of P miss versus the center point for each of those, for each of that grid, you can actually see, depending on the specific grid point or the region, that you can have a spread of about plus minus 50 MeV over C in missing momentum. So that's a fairly large spread, even in that smaller E prime theta bin. So this is sort of showing you what you have to do in terms of having the discrete theory versus to finally do the comparison. So I'll step you through this procedure. So you have E prime versus theta here. If you, let's say we have a data point that is actually directly in the center where we actually have a calculation, and if you look at the asymmetry versus missing momentum, then you have exactly that. You don't have any averaging procedure that you have to worry about. But now let's move and say we're actually at the center of these four boxes, or for this grid. And now you want to know what is the theoretical predicted asymmetry for that point. So what was done was an averaging procedure. So you have this circle here. So you then look at least in terms of the size, how far away that point is from each of the center bins for this grid. And then you have these four different calculations depending on which bin you're looking at. And then you do the calculation, and a weight is calculated by calculating how far away you are from each of those center bins. And then it is averaged using that weight, and then an uncertainty is associated with that depending on the difference between the calculated averaged asymmetry to the closest theoretical predicted asymmetry, and that gives you this uncertainty. So this is not a theoretical uncertainty, it is solely due to the fact that you have a discrete grid of calculated asymmetries, and you're doing this complicated averaging procedure to determine what that is. So then if you go to another point and look at the averaging procedure, and then you do this essentially a repetitive pattern on an event by event basis in the comparing the data to the theory until you average essentially everything over the acceptance. So that just showed you the averaging for P miss, but you also have to do this for the azimuthal angle of the deuteron with respect to the Q vector. And so this shows you the average asymmetry of this phi dq angle versus P miss for two different kinematic bins. And then finally, if you put it all together and average, this shows you E prime versus theta, and the asymmetry, or the averaged asymmetry, and this is for a particular P miss of 50 MeV over C at a phi azimuthal angle of 0 degrees, and this is P miss of 200 MeV over C. So this is after you've done all this averaging procedure for the theoretical asymmetry. On top of it, when we do the polarization for the longitudinal and transverse, because of the finite acceptance size of the detectors, you do not have a specific theta star angle. So you actually have to also average over the spin angle due to this as well. So this shows you theta star versus the missing momentum, and theta star versus omega, the energy transfer. So finally, after you do all this averaging of the theory to finally do the comparison to the data, you can actually finally show the asymmetries versus the missing momentum. And so this is for a Q squared of 0.5 GV squared. This is again polarized electron scattering off a polarized helium free, doing E prime D knockout. So we have three theoretical calculations. You have the Hanno or Lisbon group, which is the solid line. You have the dashed line, which is the Bachmann group, and the dotted line, which is the Pisa group. The solid points show you the full data point over the full omega range. And if you make a cut of omega less than 140 MeV to exclude the data above the dip region and going into the pion production region, that shows you this faked solid line here and this faked solid line here. One thing that is clear is in these calculations that we have, as you extend out to larger omega, getting into the pion production region and the resonance region, that the theoretical calculations do not include those contributions, so you expect that the theory would break down as you go to higher omega. So you do see somewhat better agreement, at least at higher p-miss, between the data and the calculations if you compare the open symbols to the state line. But what you do see is that there's a sizable difference in terms of the absolute asymmetry between the calculations and the data. And then if you look at this versus omega, or the energy transfer instead, this also shows you then you have somewhat better agreement again as you are at lower omega, but as you go to higher omega, the discrepancy becomes larger, but that's expected due to not including the pion threshold and resonance production, or resonance contributions in that area. And this shows you here the position of the quasi-elastic peak, where it is located in this data set. So one of the things clearly that you can see from this is that there's a discrepancy between the data and the calculation. And some of the calculations include 3 nucleon forces and others do not. So we can't say that it's just an absence of 3 nucleon forces or not including those. So this is, since these are state-of-the-art calculations, this is somewhat worrisome that you do see this discrepancy in terms of understanding of helium-3. Another thing you can do is, if you go to low p-miss, and this calculation was done for p-miss less than 40 MeV over C, you can assume that at low p-miss this process is like scattering, elastic scattering off a polarized deuteron within the helium-3. So if you do this, you can calculate the vector and tensor polarizations of the deuteron, and essentially the assumption that is made is that the measured helium-3 asymmetries are as if you're measuring elastic electron scattering off of a deuteron, and if you use the appropriate deuteron form factors, then you can extract these 2 polarizations. You can also use a toy model saying that helium-3 is like a quasi-deuteron plus a proton. If you use Clutch-Gordon coefficients, you can then calculate what you would expect for the vector and the tensor polarizations. And then if you actually extract it from the data using these assumptions, you get this green ellipse here with the inner and the outer being the 1 sigma and 2 sigma covariance ellipses. And then using the best theory calculation, which is the Hanover-Lisbon with the more discrete grid, it is this oval, yellow oval here. In terms of the size of the tensor polarization, within at least the ellipses, they actually agree fairly well with each other. So if you go back to the discrepancy in the asymmetries and how they then factor into this, it looks like it could be described by a discrepancy in terms of the vector polarization of the deuteron and what is coming out of the theory versus what you actually get in the data. Beyond having the E prime D asymmetries, we also, of course, have all this proton data, which we have even more statistics for. So this shows you the asymmetry versus p-miss. This is an average q squared quarter GeV squared. This is 0.35 GeV squared. The red data is with the electron, or with the target polarized along the electron beam direction here. And then the blue data is with the target polarized transverse to the electron direction. And then you actually see these very nice large asymmetries. And as you go above a certain p-miss, they cross 0 and become somewhat smaller or equal in size. So when we did this measurement, one of the things is you have 2-body and 3-body breakup in terms of the E prime. Because of the poor resolution with the big bite spectrometer, we cannot easily do the separation to separate 2-body and 3 breakup. 2-body breakup and 3-body breakup. So this shows you those combined together. Actually skip over that. There have been comparisons to the data for E prime P to the theory calculations. This is the Bachmann theory calculation. And this again is combined for the 2 regions of the 2-body and 3-body breakup. This shows you the asymmetry versus the asymmetry in terms of longitudinal and transverse. And then you have the theory calculations here. I should say in this case, the theory calculations, the reason that this is preliminary is one is that we cannot easily separate the two regions in terms of the breakup, and also the averaging of the theory calculations here is an earlier version of the averaging procedure that I highlighted with the E prime P. So to summarize, the results were published last December. So this is the publication here. The E prime P reaction is currently being analyzed, but in reality the data analysis is completed, and the only issue is that we can't easily separate these two regions. I went through the complicated averaging procedure for the data because the calculations are intensive or numerically intensive, so we can only get them over the discrete grid. In terms of additional physics focus, part of it is the 3-nucleon force, which is being done in progress. We also have data at higher Q squared, but we do not have any calculations since the Faddeev calculations themselves are non-relativistic, and as you go to higher Q squared, you have to start worrying about relativistic effects. Thank you. The Halley quasi-elastic collaboration that was involved in this experiment and their knowledge.
So I have a completely unfair question.
Unfair question?
So up to now, if we go back, we essentially have done comparison for polarized helium-free for quasi-elastic and extraction of magnetic form factor. We have done comparison on E prime P. We have comparison on E prime D. I mean, the only thing I know, if you go to larger Q squared, is that if you go to the inclusive at larger Q squared, that seems to agree better with plane wave force transformation. So that we know. So here's the unfair part of the question. Did anyone bother ever doing it for helium, polarized helium-free E prime N? As a function of missing momentum? Because I've tried to find one in Star, I've never seen the results.
That would probably know this. Are there any measurements from DCAL?
No, from you guys have noticed GN.
Sure, we did the E prime N, but with a different polarization direction.
But never as a function of PM, that's what I'm asking.
So for the Halley GN measurement we did with Big Bright, we were very careful to limit the range in PMIS, and we had MESOC do exactly that averaging. For the very reasons Vince is showing, that asymmetry does change signs. So MESOC did it.
Here even at low missing momentum it doesn't work. So what? Here even at low missing momentum it doesn't work. So just limiting yourself to a small region of PM might not be sufficient. So did anyone ever check it? Really, rather than just averaging in theory and in data? I mean, here even at PM equals 0.
I already knew GEN, and that's the whole problem, right? So I'm using the polarized helium-3 data to extract GEN. We know that as I go out in PMIS, I do have a dependence, so we limited ourselves with a smaller PMIS. But yeah, if there was an offset, it got embedded in the extraction of GEN.
I agree. That's why I worry.
Yeah, yes. And that's why we need both helium and deuterium.
Yeah, that unfortunately was not. And GEN was
So Vince, looking at this plot, it seems to me, if you assume that the deuteron is the, well, it almost doesn't matter whether the deuteron is the active particle in this or not, but by picking up the PD state, you're selecting the worst component of the helium-3 wave function because you're selecting the component.
Yeah, that's what we wanted to do.
Proton spin is very active.
Yes, that's what we wanted to do.
So in some sense, I mean, because if I look at this, I say, gee, it doesn't look like helium-3 is a very good neutron target. Because of the at least not with the precision of the calculations. B prime P looked a little better. Not perfect, but.
Yeah, and well, that's an early comparison, so yeah, that's the only reason it's preliminary, is the averaging isn't finalized on that.
So, I mean, it sort of comes back to the earlier discussion. I mean, can you make any conclusions about the precision with which we can extract neutron information from helium-3?
You know, that's what I asked Oleg when I was at the Few Body Workshop 2 weeks ago. And, you know, I didn't get a good answer from him. Because I said, well, with this information, if you had to go back, how would that change how we understand the uncertainty that we've been using for, you know, at least a decade now? And he basically said, well, he wasn't sure, and he said at this point, you know, the codes and the people that did the analysis, you know, are gone now, so he's not even sure how easy it would be to go back and redo that, you know, based on this information.
And so are you willing to stand up in a room of 200 people and say that it's ridiculous to build a line collider with only polarized helium-3?
I think some people think that. I mean, clearly, this tells us that there's something we don't understand with helium-3, and you know, so we definitely can't improve our statistical or our extraction, you know, uncertainties at this point without understanding this better. And unfortunately, talking to theorists, they're like, well, this is what we did, we don't know why at this point. And so I don't know.
Any more questions? Well, that's the end of our session, and that's the end of the meeting. So thank you all for staying until the very end.
Excellent loaded question. My answer, yes, I do. Extracted to the end, came out of a waffle effect, or a few runs, until we had to say you're actually